What lies beyond the boundaries of everything we know? This question has puzzled humanity for millennia, driving scientific inquiry to the edge of comprehension. From the mind-bending concept of a cyclic universe to the possibility of extra dimensions predicted by string theory, our understanding of reality continues to evolve. We stand on the precipice of revolutionary ideas, dark energy shaping cosmic destiny, holographic principles challenging our perception of space, and quantum fluctuations birthing new universes. As we explore these frontiers, we confront big questions about our place in existence. Are we part of a massive multiverse, or could our reality be a simulation? The observable universe encompasses all the matter and energy we can detect from Earth, stretching out in every direction to the farthest limits of our view. This cosmic horizon is not a physical boundary, but rather the extent to which light has had time to reach us since the birth of the universe approximately 13.8 billion years ago. Light, though incredibly fast, is not instantaneous. It takes time for the radiance of distant stars and galaxies to traverse the vast cosmic distances and arrive at our telescopes. The most distant objects we can observe are those whose light has been traveling toward us for nearly the entire age of the universe. This means that when we peer into the depths of space, we are also looking back in time. The light from the edge of the observable universe began its journey when the cosmos was in its infancy, just a few 100,000 years old. As we look closer to home, we see celestial objects as they appeared more recently. The observable universe is constantly expanding as light from ever more distant regions finally reaches Earth. However, due to the expansion of space itself, there are regions of the universe that we will never be able to see, no matter how long we wait. These areas lie beyond our cosmic horizon, forever out of reach, making the observable universe a finite glimpse of a potentially infinite cosmic expanse. The observable universe stretches an immense 93 billion light-years in diameter. This vast expanse represents the farthest distance we can see in any direction from Earth, limited by the speed of light and the age of the universe. Light from the most distant objects has taken nearly 14 billion years to reach us, traveling since shortly after the Big Bang. However, due to the expansion of space itself during this journey, those objects are now much farther away than 14 billion light-years. This cosmic horizon continues to grow as time passes, with more distant regions becoming visible to us. Yet, there likely exists much more universe beyond what we can observe, potentially stretching to infinity. Our view is fundamentally limited by the finite age of the universe and the constant speed of light. The sheer scale of the observable universe challenges human comprehension, encompassing countless galaxies, each home to billions of stars and planets. It serves as a humbling reminder of our place within the cosmic tapestry. The observable universe has boundaries, not because space itself ends, but due to the finite speed of light and the age of the universe. Light from the farthest reaches of space has been traveling towards us for billions of years, yet there are regions so distant that their light hasn't had time to reach us since the Big Bang. This cosmic horizon, known as the observable universe, extends approximately 93 billion light-years in diameter. Beyond this limit, we cannot see or detect anything, as the light from those regions has not yet had sufficient time to reach Earth. It's important to note that this boundary is not static. It continues to expand as time passes and more distant light reaches us. The expansion of the universe further complicates our observations. As the universe expands, light from distant objects is stretched, shifting towards longer wavelengths in a phenomenon called redshift. For the most distant objects, this redshift is so extreme that their light becomes undetectable to our instruments. Additionally, the early universe was opaque for its first 380,000 years, filled with a dense fog of hydrogen plasma. Only after this period did the universe become transparent, allowing light to travel freely. This event, known as recombination, creates another barrier to our observations, as we cannot directly see anything that occurred before this time using electromagnetic radiation. The cosmic horizon marks the boundary of our observable universe, defining the farthest reaches of space from which light has had time to reach Earth since the beginning of the universe. This horizon is not a physical barrier, but rather a limit imposed by the finite speed of light and the age of the universe. Light travels at a constant speed, taking time to cross vast cosmic distances. The farther we look into space, the further back in time we see. The cosmic horizon represents the most distant light that has had enough time to reach us, about 13.8 billion years. The observable universe is everything within this cosmic horizon, a spherical volume centered on Earth with a radius of about 46 billion light-years. This size accounts for the expansion of space itself, which allows the observable universe to be larger than one might expect based solely on the age of the universe and the speed of light. Beyond the cosmic horizon lies the unobservable universe, regions so distant that their light has not yet had time to reach us. As time passes, more of the universe becomes observable, gradually pushing our cosmic horizon outward and expanding our view of the cosmos. Our understanding of the universe's size has undergone a dramatic transformation throughout history. Ancient civilizations believed the Earth was the center of a relatively small cosmos, with the stars as fixed points on a celestial sphere. This geocentric model persisted for centuries, limiting our concept of the universe's true scale. The scientific revolution brought significant changes. In the 16th century, Copernicus proposed a heliocentric model, placing the Sun at the center of our solar system. This shift expanded our cosmic perspective, but the universe was still thought to be much smaller than we know it to be today. A major leap came in the early 20th century when Edwin Hubble proved that the Milky Way was not the entire universe, but just one of many galaxies. His observations of distant nebulae revealed a vast cosmos beyond our own galaxy, expanding our understanding of the universe's size by orders of magnitude. Modern astronomy and space exploration have further expanded our cosmic horizons. We now know the observable universe spans approximately 93 billion light-years in diameter, containing hundreds of billions of galaxies, each home to hundreds of billions of stars. This immense scale, unimaginable to our ancestors, continues to grow as our instruments and knowledge improve, revealing an ever-expanding cosmos that challenges our comprehension. Astronomers employ a diverse array of sophisticated tools and technologies to unravel the mysteries of the observable universe. At the forefront are powerful optical telescopes, both ground-based and spaceborne, that capture visible light from distant celestial objects. These include behemoths like the 30-meter telescope and the orbiting Hubble Space Telescope, which have revolutionized our understanding of cosmic structures. Beyond visible light, astronomers harness the entire electromagnetic spectrum. Radio telescopes, such as the Very Large Array in New Mexico, detect radio waves emitted by stars, galaxies, and other cosmic phenomena. X-ray and gamma-ray observatories, like the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope, unveil high-energy processes in the universe, from black holes to supernovae. Infrared telescopes, exemplified by the James Webb Space Telescope, peer through cosmic dust to reveal stellar nurseries and distant galaxies. Ultraviolet telescopes uncover hot, young stars and active galactic nuclei. These multi-wavelength observations provide a comprehensive view of celestial objects and events. Complementing these traditional tools, astronomers now utilize cutting-edge technologies like adaptive optics to counteract atmospheric distortion, interferometry to combine multiple telescopes into virtual giant instruments, and advanced computer simulations to model cosmic processes. Gravitational wave detectors like LIGO have opened an entirely new window into the universe, allowing us to hear cosmic collisions and explore the nature of space-time itself. The expansion of the universe fundamentally shapes our view of distant cosmic objects. As space itself stretches, light from faraway galaxies and stars must travel through an ever-expanding medium. This expansion causes the light to be stretched, shifting its wavelength towards the red end of the spectrum. We call this phenomenon redshift, and it becomes more pronounced the farther away an object is from us. This cosmic expansion presents both challenges and opportunities for astronomers. On one hand, it limits our ability to see the most distant objects clearly, as their light becomes increasingly redshifted and fainter. Some objects are so far away that their light has been stretched beyond the visible spectrum entirely, requiring specialized infrared telescopes to detect them. However, the expansion also provides a valuable tool for measuring cosmic distances. By analyzing the degree of redshift in an object's light, scientists can calculate how far away it is and how fast it's moving away from us. This information is crucial for mapping the structure and history of the universe. The expansion of the universe also means that there's a limit to how far we can see, known as the observable universe. Beyond this cosmic horizon, light from more distant objects hasn't had enough time to reach us since the beginning of the universe. As the universe continues to expand, some galaxies will eventually move beyond our cosmic horizon, becoming forever invisible to us. The cosmic microwave background is a crucial piece of evidence that helps us understand the early universe and its current limits. This faint glow of radiation permeates all of space and represents the oldest light in the universe, dating back to about 380,000 years after the Big Bang. When we observe the cosmic microwave background, we are essentially looking at the edge of the observable universe. It acts as a cosmic horizon beyond which we cannot see directly. This radiation provides a snapshot of the universe when it first became transparent to light, marking the point where the universe cooled enough for atoms to form. The uniformity of the cosmic microwave background across the sky supports the idea of cosmic inflation, a period of rapid expansion in the early universe. This expansion helps explain why the universe appears flat and homogeneous on large scales, addressing fundamental questions about the universe structure. By studying tiny fluctuations in the cosmic microwave background, scientists can infer information about the composition and evolution of the universe. These fluctuations serve as seeds for the cosmic structures we see today, from galaxies to galaxy clusters, providing insight into how the universe transformed from a nearly uniform state to the complex cosmos we observe now. The multiverse theory proposes that our universe is not alone, but part of a vast collection of universes existing simultaneously. This concept suggests that beyond the boundaries of our observable cosmos lie countless other universes, each potentially with its own unique laws of physics, fundamental constants, and possibly even forms of life. According to this theory, these universes might be separated by higher dimensions or exist in parallel, like sheets of paper stacked together. Some versions of the multiverse theory stem from the principles of quantum mechanics, where every possible outcome of a quantum event could create a new universe. Others arise from string theory and the idea of eternal inflation, where new universes continually bubble into existence. The multiverse concept challenges our understanding of reality and raises profound questions about the nature of existence. If true, it would mean that everything we know, from the laws of physics to the very fabric of space and time, might only apply to our particular universe. Other universes could have entirely different properties, from subtle variations to radically alien configurations. While the multiverse theory is fascinating, it remains highly speculative and currently impossible to test directly. Scientists continue to explore its implications and search for indirect evidence that might support or refute this mind-bending idea about the structure of reality. The multiverse theory proposes the existence of multiple universes beyond our own, challenging the traditional single-universe model. While the single-universe concept suggests that our observable cosmos is all that exists, the multiverse theory opens up a vast array of possibilities. In the multiverse scenario, our universe is just one of many, potentially infinite, universes existing simultaneously. These universes might have different physical laws, constants, or initial conditions, leading to diverse realities. Some theories suggest these universes could be separated by higher dimensions or exist in parallel. The single universe model, by contrast, posits that our observable universe is unique and self-contained. It assumes that the physical laws and constants we observe are universal and unchanging throughout all of space and time. One key difference lies in how these models address fine-tuning questions. The single universe model struggles to explain why our universe seems perfectly tuned for life, while the multiverse theory suggests that in a vast array of universes, some will inevitably have conditions suitable for life to emerge. This shift in perspective has profound implications for our understanding of cosmic origins and the nature of reality itself. The concept of a multiverse is supported by several scientific theories and principles. Quantum mechanics, a fundamental theory in physics, suggests the existence of multiple parallel universes through its many worlds interpretation. This interpretation proposes that every possible outcome of a quantum event occurs in a separate universe, leading to an infinite number of parallel realities. String theory, another prominent framework in theoretical physics, also lends support to the multiverse idea. It postulates that our universe is just one of many universes, each with its own set of physical laws and constants. These universes are often described as existing in higher dimensions, beyond the four we can directly observe. Inflationary theory, which explains the rapid expansion of the early universe, provides another avenue for multiverse speculation. Some versions of this theory suggest that inflation continues eternally in some regions of space, constantly creating new universes in a process called eternal inflation. The anthropic principle also plays a role in multiverse theories. It addresses the seemingly fine-tuned nature of our universe, suggesting that out of countless universes with different properties, we naturally find ourselves in one capable of supporting life. This principle helps explain why our universe appears so well suited for our existence without resorting to supernatural explanations. Scientists have proposed several different types of multiverses, each with its own unique characteristics and implications for our understanding of reality. The concept of multiple universes has gained traction in theoretical physics and cosmology over recent decades. One widely discussed type is the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of a quantum event occurs in a separate universe. This leads to an infinite number of parallel universes branching off from each quantum decision point. Another proposal is the inflationary multiverse, based on the theory of cosmic inflation. This model suggests that our universe is just one of many bubble universes that formed during the rapid expansion of space in the early moments after the Big Bang. Each of these bubbles could have different physical laws and constants. String theory, a candidate for a unified theory of physics, has also given rise to the idea of a multiverse. The landscape of string theory allows for an enormous number of possible universes, each with its own set of physical laws. Some scientists estimate this number could be as high as 10 to the power of 500 distinct universes. The bubble universe concept is a fascinating aspect of multiverse theory that proposes our universe is just one of many universes existing simultaneously. In this model, each universe is likened to a bubble floating in a vast cosmic sea. These bubbles can form, expand, and potentially even collide with one another. According to this idea, during the earliest moments of cosmic creation, the fabric of space-time underwent a period of rapid expansion known as inflation. This expansion was driven by a hypothetical field called the inflation field. As this field decayed, it released enormous amounts of energy, giving birth to our observable universe. However, the bubble universe concept suggests that this process of inflation and decay might not have happened uniformly everywhere. Instead, different regions of space could have experienced varying rates of inflation. leading to the formation of separate bubble universes. Each of these bubbles would have its own laws of physics, fundamental constants, and potentially even different dimensions. This concept opens up mind-boggling possibilities. There could be an infinite number of these bubble universes, each with its own unique characteristics. Some might be similar to our own, while others could be wildly different, perhaps incapable of supporting any form of life as we know it. The bubble universe idea offers a potential explanation for the apparent fine-tuning of our universe, suggesting that we simply happen to exist in a bubble with the right conditions for our form of life to emerge. Quantum mechanics and the concept of multiple universes are intricately linked through the many worlds interpretation. This theory, proposed by physicist Hugh Everett, suggests that every quantum event creates a branching of reality into different universes. When we observe quantum particles, they exist in a state of superposition, meaning they can be in multiple states simultaneously. However, upon measurement, we only see one specific outcome. The many worlds interpretation posits that all possible outcomes actually occur, each in a separate universe. This mind-bending idea implies that our universe is just one of countless others, each representing a different outcome of quantum events. Every decision we make, every coin flip, and every quantum fluctuation could spawn new universes. These parallel worlds would be nearly identical to ours, differing only in the outcome of that specific quantum event. While this interpretation remains controversial, it offers a fascinating perspective on the nature of reality and our place within it. It suggests that the universe we experience is just one thread in an infinitely complex tapestry of possibilities, all stemming from the strange behavior of quantum particles. The many worlds interpretation is a fascinating concept in quantum physics that challenges our understanding of reality. Proposed by physicist Hugh Everett in the 1950s, this theory suggests that every time a quantum event occurs, the universe splits into multiple parallel realities. In this view, all possible outcomes of quantum measurements actually happen, each in a separate universe. For example, when we measure the spin of an electron, instead of it randomly choosing to be either up or down, both outcomes occur simultaneously in different universes. This means that for every decision we make, every coin we flip, and every quantum event that takes place, a new universe branches off. The implications of this interpretation are mind-boggling. It suggests that there are countless versions of ourselves living out different lives based on different choices and outcomes. These parallel universes are thought to be entirely separate and unable to interact with each other, which is why we only experience one reality. While the many worlds interpretation offers a solution to some paradoxes in quantum mechanics, it remains highly controversial. Many scientists find it difficult to accept the idea of an ever-multiplying number of universes. However, it continues to intrigue physicists and philosophers alike, pushing the boundaries of our understanding of quantum reality and the nature of existence itself. The concept of parallel universes, also known as the multiverse theory, suggests that our universe might be one of many existing simultaneously. While this idea remains theoretical, scientists have proposed several ways these universes could potentially interact. One possibility is through quantum entanglement. This phenomenon, observed in our own universe, allows particles to be connected regardless of distance. Some physicists speculate that quantum entanglement might extend beyond our universe, creating subtle links between parallel realities. Another theoretical interaction involves cosmic collisions. Some models propose that universes could exist as membranes or branes floating in a higher dimensional space. If these branes collide, it could cause ripples in both universes, potentially observable as gravitational waves or unusual cosmic events. Wormholes offer another hypothetical means of interaction. These theoretical tunnels through space-time might connect not just distant parts of our universe, but also bridge separate universes. However, the existence of wormholes remains unproven, and their stability and traversability are subjects of ongoing debate in the scientific community. While the concept of a multiverse is intriguing, direct observational evidence remains elusive. However, several indirect lines of evidence and theoretical considerations lend support to the idea. One potential piece of evidence comes from cosmic microwave background radiation. Some scientists argue that certain anomalies in this ancient light could be explained by the influence of other universes. These include unexpected cold spots and alignments in the radiation pattern that are difficult to account for in a single universe model. Quantum mechanics also provides theoretical backing for the multiverse concept. The many worlds interpretation suggests that every quantum event creates multiple realities, potentially giving rise to countless parallel universes. While we cannot directly observe these other worlds, the mathematics underlying quantum theory is consistent with their existence. String theory, a candidate for a unified theory of physics, often predicts the existence of multiple universes as a natural consequence of its framework. The theory requires extra dimensions, and some versions suggest that our universe might be just one of many brains floating in a higher dimensional space. Although string theory remains unproven, its mathematical consistency adds weight to multiverse ideas. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings, which are incredibly small, about 100 billion times smaller than an atomic nucleus, are thought to vibrate in different ways, giving rise to all the particles and forces we observe in nature. According to string theory, our universe might have as many as 10 or 11 dimensions, most of which are curled up and invisible to us. This concept challenges our everyday understanding of reality, which only perceives 3 spatial dimensions and 1 dimension of time. The extra dimensions proposed by string theory could explain why gravity appears so much weaker than the other fundamental forces of nature. String theory attempts to unify all the known forces in the universe, including gravity, into a single, coherent framework. This makes it a promising candidate for the long-sought theory of everything, which would explain all physical phenomena in the universe from the smallest subatomic particles to the largest cosmic structures. However, string theory remains highly speculative and unproven. Scientists have yet to find experimental evidence to support its predictions, and some critics argue that it might be untestable. Despite these challenges, string theory continues to fascinate physicists and cosmologists as they seek to understand the deepest mysteries of our universe. String theory, one of the most intriguing and complex ideas in modern physics, proposes a universe with far more dimensions than we can perceive. While our everyday experience is limited to 3 spatial dimensions and 1 dimension of time, string theory suggests that reality might encompass 10 or 11 dimensions in total. These extra dimensions are thought to be tightly curled up and incredibly small, existing at scales far tinier than even subatomic particles. The idea is that these hidden dimensions could explain many of the mysteries that continue to puzzle physicists, such as the nature of dark matter and the unification of fundamental forces. The exact number of dimensions proposed by string theory has evolved over time. Initially, the theory required 26 dimensions, which was later refined to 10. An extension of string theory, known as M theory, proposes 11 dimensions. These additional dimensions are not just mathematical constructs, but are believed to have real physical significance, potentially shaping the very fabric of our universe. Understanding these extra dimensions is crucial for string theory's attempt to reconcile quantum mechanics and general relativity, 2 pillars of modern physics that have long resisted unification. While we cannot directly observe or interact with these extra dimensions, their existence could have profound implications for our understanding of the cosmos and the fundamental nature of reality. In string theory, brains are fundamental objects that exist in multiple dimensions. The term brain is short for membrane, though these structures can have various dimensions. Brains can be thought of as sheets or surfaces that extend through space and time, serving as the foundation for our universe and potentially others. String theory proposes that our universe might be a three-dimensional brain floating in a higher dimensional space. This larger space, often called the bulk, could contain other brains, each representing a distinct universe. These universes might be parallel to ours, separated by extra dimensions we cannot directly observe or interact with. The concept of brains offers a fascinating explanation for the multiverse theory. It suggests that what we perceive as our entire cosmos might be just one of many universes, each existing on its own brain. These universes could have different physical laws, constants, or even different numbers of dimensions. Interactions between brains could potentially explain some cosmic phenomena. For instance, some physicists have proposed that the Big Bang might have been caused by a collision between two brains. This idea opens up new avenues for understanding the origin and evolution of our universe, as well as the possibility of other universes beyond our own. Extra dimensions could be hidden from our everyday experience in several intriguing ways. One possibility is that these dimensions are incredibly small, curled up into tight loops that are far too tiny for us to detect with our current technology. Imagine a tightrope walker on a wire. From a distance, the wire appears to be a one-dimensional line, but up close, an ant could walk around the circumference of the wire, revealing an extra dimension. Another concept suggests that extra dimensions might be vast but inaccessible to us. Our universe could be like a sheet of paper floating in a much larger space, with our everyday experiences confined to the surface of that sheet. We would be unaware of the space above or below us, just as a two-dimensional being on a flat plane would be oblivious to the concept of height. Some theories propose that extra dimensions could be separated from our familiar four-dimensional spacetime by enormous amounts of energy. This would mean that under normal circumstances, matter and light would be unable to enter or interact with these hidden realms, making them effectively invisible to us. Lastly, these extra dimensions might manifest in ways we do not yet recognize. Our brains and sensory organs have evolved to perceive and interpret a four-dimensional universe. It is possible that evidence of extra dimensions surrounds us, but we lack the cognitive framework to process and understand this information. Much like a colorblind person cannot distinguish certain hues that are obvious to others. M theory represents a groundbreaking advancement in theoretical physics, building upon and unifying various versions of string theory. This comprehensive framework proposes that our universe consists of 11 dimensions, expanding beyond the 10 dimensions suggested by earlier string theories. At its core, M theory posits that the fundamental components of the universe are not point-like particles, but rather vibrating, one-dimensional strings. These strings can oscillate in different ways, giving rise to the diverse particles and forces we observe in nature. M theory takes this concept further by introducing two-dimensional membranes, or brains, which can exist in multiple dimensions. One of the most intriguing aspects of M theory is its potential to reconcile quantum mechanics with general relativity, two pillars of modern physics that have long seemed incompatible. By providing a unified description of all fundamental forces and particles, M theory offers a promising path toward a theory of everything, a long-sought goal in physics. While M theory remains highly speculative and lacks experimental evidence, it continues to captivate physicists with its elegant mathematical structure and its potential to unlock the deepest mysteries of the cosmos. As scientists work to develop testable predictions from M theory, it remains at the forefront of our quest to understand the fundamental nature of reality. The concept of extra dimensions could revolutionize our understanding of gravity. While we perceive and interact with three spatial dimensions and one dimension of time, some theories suggest our universe might contain additional hidden dimensions. These extra dimensions could explain why gravity appears weaker than other fundamental forces. In this scenario, gravity might not be inherently weaker, but rather spread out across these extra dimensions. This would mean that gravity is just as strong as other forces, but we only experience a fraction of its true strength in our observable four-dimensional space-time. The rest of its influence could be dispersed into these hidden dimensions, making it seem comparatively weak from our perspective. This idea ties into string theory, which proposes that the fundamental constituents of the universe are tiny, vibrating strings of energy. These strings would require extra dimensions to vibrate in ways that could produce all the particles and forces we observe. If true, gravity could be unified with the other fundamental forces, solving a long-standing puzzle in physics. Understanding extra dimensions could also shed light on other cosmic mysteries. It might help explain dark matter, dark energy, or even the nature of black holes. By expanding our view of the universe beyond the dimensions we can directly observe, we might uncover new insights into the fundamental workings of reality itself. Scientists are employing various ingenious methods to search for evidence of extra dimensions beyond the four we experience in our everyday lives. One approach involves using powerful particle accelerators like the Large Hadron Collider at CERN. By smashing particles together at incredibly high energies, researchers hope to create conditions where particles might momentarily escape into extra dimensions, leaving behind a telltale signature of missing energy in the detectors. Another experimental avenue explores the possibility that gravity might behave differently at very small scales due to the influence of extra dimensions. Scientists use extremely sensitive instruments to measure gravitational forces between objects separated by tiny distances, looking for deviations from the expected behavior of gravity in 3 spatial dimensions. Astronomers are also joining the hunt, searching the cosmos for signs of extra dimensions. They analyze the cosmic microwave background radiation, the afterglow of the Big Bang, for subtle patterns that could indicate the presence of additional spatial dimensions in the early universe. Some researchers even propose that certain properties of black holes or the expansion rate of the universe might be influenced by extra dimensions, prompting detailed observations of these phenomena. These diverse experimental approaches demonstrate the creativity and determination of scientists in their quest to unravel the fundamental nature of our reality. While no conclusive evidence of extra dimensions has been found yet, these ongoing experiments continue to push the boundaries of our understanding and may one day reveal new aspects of the universe hidden from our everyday perception. The discovery of extra dimensions would revolutionize our understanding of the cosmos and potentially redefine what we consider to be beyond our universe. These hidden dimensions, if proven to exist, could explain many mysteries in physics and open up new realms of possibility for the structure of reality. Extra dimensions might provide a framework for parallel universes or alternate realities. They could exist alongside our familiar 3 spatial dimensions and 1 time dimension, but remain invisible to us in our everyday experience. These additional dimensions might be compactified, curled up so tightly that they are undetectable at the macroscopic scale, yet play a crucial role in the fundamental workings of the universe. The existence of extra dimensions could also shed light on the nature of dark matter and dark energy, 2 of the most perplexing aspects of modern cosmology. These elusive components might reside or interact primarily within these hidden dimensions, explaining their apparent invisibility in our observable universe. Furthermore, extra dimensions could potentially connect our universe to others, forming a vast multiverse. This concept challenges our notion of what lies beyond our cosmic horizon, suggesting that our universe might be just one of many interconnected realms, each with its own physical laws and properties. The discovery of extra dimensions would thus expand our cosmic perspective, forcing us to reconsider the very nature of reality and our place within it. The concept of an edge to the universe is one of the most intriguing and challenging ideas in cosmology. Current scientific understanding suggests that the universe does not have a physical edge in the way we typically think of boundaries. Instead, the universe is believed to be infinite, or, if finite, to have a shape that wraps around itself. Our observations indicate that the universe is expanding in all directions, with every point moving away from every other point. This expansion is not happening within some larger space, but is the stretching of space itself. As far as we can see in any direction, the universe appears to be uniform and follows the same physical laws. If the universe is indeed infinite, the question of an edge becomes meaningless. An infinite universe would extend forever in all directions without any boundary. On the other hand, if the universe is finite, it might be what scientists call positively curved, like the surface of a sphere. In this case, traveling in one direction would eventually bring you back to your starting point, similar to how circumnavigating the Earth works. It is important to note that these ideas refer to the observable universe, which is limited by the distance light has traveled since the Big Bang. What lies beyond the observable universe remains a subject of theoretical speculation and ongoing research in cosmology. When scientists discuss the edge of the universe, they are not referring to a physical boundary in space. Instead, they are describing the farthest distances we can observe from Earth. This limit is called the observable universe, and it is determined by the speed of light and the age of the universe. Light from the most distant objects has taken nearly 14 billion years to reach us, traveling since shortly after the Big Bang. Beyond this cosmic horizon, we cannot see or detect anything because the light from those regions has not had enough time to reach Earth. This does not mean nothing exists beyond this point. It simply marks the current limit of our observations. The concept of an edge becomes even more complex when we consider the shape of the universe. Many scientists believe the universe might be infinite in size, or it could have a curved geometry that wraps around on itself, much like the surface of a sphere. In either case, there would be no true edge to space itself. As our technology improves and we develop more sophisticated ways of observing the cosmos, we may be able to push the boundaries of our observable universe further. However, due to the expansion of space itself, some regions will forever remain beyond our view, continuing to recede faster than the speed of light relative to our position. The expanding universe presents a fascinating paradox when we consider its edge. In reality, the universe has no discernible edge in the way we typically think of boundaries. As the universe expands, it's not growing into some pre-existing space, but rather creating new space everywhere, all the time. This expansion occurs uniformly throughout the cosmos, with every region of space stretching away from every other region. Imagine a loaf of raisin bread rising in an oven. As the dough expands, each raisin moves away from every other raisin, but there's no center or edge to this expansion. Similarly, our universe's expansion doesn't have a center or an edge. From our vantage point on Earth, we observe distant galaxies moving away from us in all directions, but observers in those galaxies would see the same thing from their perspective. This uniform expansion is a fundamental property of space itself. What we often refer to as the edge of the observable universe is actually the limit of what we can see due to the finite speed of light and the age of the universe. Beyond this cosmic horizon, the universe likely continues, expanding just as it does in our observable region, stretching into distances we cannot yet fathom or observe. The observable edge of our universe marks the limit of what we can see from Earth, but it doesn't necessarily represent the true extent of the cosmos. Beyond this boundary, the universe likely continues, possibly stretching infinitely. Current scientific theories suggest that the region beyond our observable universe might be remarkably similar to what we can see. It could contain countless more galaxies, stars, and planets, forming structures much like those we observe. This vast expanse might hold an unimaginable number of potentially habitable worlds and perhaps even other forms of life. However, some cosmologists propose more exotic possibilities. The concept of the multiverse suggests that our universe might be just one of many, each with its own set of physical laws and constants. These parallel universes could exist alongside ours, separated by higher dimensions we cannot directly perceive. Another intriguing idea is that the very nature of space, time, and matter might change beyond our cosmic horizon. Some theories predict that the fundamental forces governing our observable universe could behave differently in distant regions, leading to environments that defy our current understanding of physics. Cosmological models offer varying perspectives on the universe's boundaries, each with intriguing implications. The most widely accepted model today, the lambda cold dark matter model, suggests that the observable universe is a tiny fraction of a much larger, possibly infinite cosmos. In this view, there is no edge or boundary to space itself, but rather a limit to how far we can see due to the finite speed of light and the age of the universe. Some alternative models propose a finite universe with a specific shape, such as a three-dimensional sphere or a complex geometric structure like a dodecahedron. In these scenarios, if you were to travel in one direction long enough, you might eventually return to your starting point, similar to circumnavigating the Earth. Other theories, including some interpretations of string theory, suggest the existence of multiple universes or dimensions beyond our own. These models describe our universe as one of many bubbles in a vast multiverse, each with its own physical laws and properties. Regardless of the model, a key point to remember is that when cosmologists talk about the edge of the universe, they often refer to the boundary of the observable universe, not necessarily a physical border of all that exists. This distinction highlights the ongoing quest to understand the true nature and extent of our cosmic home. The cosmic web is the largest known structure in the universe, a vast network of interconnected filaments composed of dark matter and galaxies. This intricate pattern stretches across the cosmos, forming a framework that defines the large-scale structure of the universe. Imagine the cosmic web as an enormous, three-dimensional spider web spanning billions of light years. The filaments of this web are made up of dark matter, an invisible substance that interacts only through gravity. These dark matter strands act as cosmic highways, guiding the formation and movement of visible matter, such as galaxies and galaxy clusters. At the intersections of these filaments, we find massive clusters of galaxies. These clusters are like cosmic metropolises, housing hundreds or thousands of galaxies bound together by gravity. Between these dense nodes are vast, nearly empty regions called voids, analogous to the spaces between the strands of a spider's web. The cosmic web plays a crucial role in the evolution of the universe. It influences how galaxies form, grow, and merge over cosmic time. By studying this grand structure, scientists gain insights into the distribution of matter in the universe and the fundamental forces that shape cosmic evolution. The cosmic web serves as a roadmap of the universe's past, present, and future, helping us understand our place in the grand cosmic tapestry. Voids and filaments in the cosmic web offer crucial insights into the structure and boundaries of our universe. These vast cosmic features, spanning millions of light years, reveal the intricate architecture of space on the largest scales we can observe. Cosmic voids are enormous, nearly empty regions of space that contain very few galaxies. They can stretch for hundreds of millions of light years across, dwarfing even the largest galaxy clusters. Filaments, on the other hand, are the dense, thread-like structures that connect galaxy clusters and form the boundaries of cosmic voids. Together, these elements create a cosmic web that resembles a colossal, three-dimensional spider's web stretching across the observable universe. The distribution and characteristics of voids and filaments provide valuable information about the early universe and its evolution. They are thought to have originated from tiny fluctuations in the density of matter shortly after the Big Bang. Over billions of years, gravity caused matter to clump together, forming filaments and leaving behind vast, empty spaces. Studying these structures helps cosmologists understand the limits of our universe in several ways. The size and number of voids and filaments give us clues about the total amount of matter in the universe and how it is distributed. This information, in turn, helps scientists refine their models of cosmic expansion and the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. By mapping these immense structures, we gain a better understanding of the scale and composition of the cosmos, pushing the boundaries of our knowledge about the universe's ultimate limits. Dark matter exerts a profound influence on the structure and potential boundaries of the universe, despite its mysterious nature. This invisible substance, which does not interact with light or other forms of electromagnetic radiation, accounts for approximately 85% of all matter in the cosmos. Its gravitational effects shape the distribution of visible matter, guiding the formation of galaxies and larger cosmic structures. On the grandest scales, dark matter forms an intricate cosmic web that spans the observable universe. This web consists of vast filaments and sheets of dark matter, with dense clusters at their intersections. Ordinary matter, such as stars and galaxies, tends to collect within this framework, following the gravitational contours laid out by dark matter. This process has been ongoing since the early universe, with dark matter acting as a scaffolding for cosmic structure formation. The presence of dark matter also affects our understanding of the universe's potential boundaries. Its gravitational influence extends far beyond visible matter, creating enormous halos around galaxies and galaxy clusters. These halos stretch the gravitational reach of cosmic structures, blurring the lines between distinct systems and contributing to the interconnected nature of the cosmos. Furthermore, dark matter plays a crucial role in ongoing debates about the universe's overall shape and whether it has definable boundaries. Its distribution and total quantity influence calculations of the universe's mass and energy content, which in turn affect models of cosmic expansion and the ultimate fate of the universe. As scientists continue to study dark matter, they hope to gain deeper insights into these fundamental questions about the nature and limits of our cosmic home. The concept of an infinite universe challenges our everyday understanding of space and boundaries. When we say the universe might be infinite, we mean it extends endlessly in all directions, with no edge or border to be found. This idea suggests that no matter how far we travel, we would never reach a point where space simply stops. In an infinite universe, space would continue forever, containing a limitless number of galaxies, stars, and planets. It's important to note that this doesn't necessarily mean the universe contains every possible arrangement of matter or that it repeats exactly. Instead, it implies an unending expanse of space filled with cosmic structures. This concept raises intriguing questions about the nature of reality and our place within it. If the universe is truly infinite, it would mean that our observable universe, vast as it is, represents only an infinitesimally small fraction of what exists. The idea of infinity in this context stretches the limits of human comprehension and continues to be a subject of intense scientific inquiry and philosophical debate. While the notion of an infinite universe aligns with some theoretical models, it's crucial to understand that we currently lack definitive evidence to confirm or refute this possibility. Ongoing research in cosmology and physics continues to explore the true nature and extent of our universe. The concepts of an infinite universe and a finite but unbounded universe are both mind-bending ideas that challenge our everyday understanding of space. An infinite universe extends endlessly in all directions with no edge or boundary. It would contain an unlimited amount of matter and energy stretching on forever. In such a universe, no matter how far you travel, you would always find more space, more galaxies, and more cosmic structures. A finite but unbounded universe, on the other hand, has a limited volume but no boundary or edge. This concept is often compared to the surface of a sphere. Just as you can travel around the Earth's surface without ever reaching an edge, you could theoretically travel through a finite but unbounded universe and return to your starting point. However, unlike the Earth's surface, this would happen in three-dimensional space. One key difference between these two models lies in their geometry. An infinite universe would likely have a flat or open geometry, while a finite but unbounded universe would have a curved geometry, similar to the surface of a sphere but in higher dimensions. This curvature would be imperceptible on small scales but would become apparent over vast cosmic distances. Another crucial distinction is in their implications for the total amount of matter and energy in the universe. An infinite universe would contain an infinite amount of matter and energy, while a finite but unbounded universe would contain a finite, albeit possibly immense amount. This difference has profound implications for our understanding of the universe's structure, evolution, and ultimate fate. The concept of an infinite universe has intrigued scientists and philosophers for centuries. Observational evidence both supports and challenges this idea, making it a topic of ongoing debate in cosmology. One piece of evidence that seemingly supports an infinite universe is the observed flatness of space. Measurements from cosmic microwave background radiation suggest that the universe is remarkably close to being flat on large scales. In many cosmological models, a flat universe extends infinitely in all directions. However, this observation alone does not conclusively prove that the universe is infinite. Our observations are limited by the cosmic horizon, the farthest distance from which light has had time to reach Earth since the Big Bang. This horizon represents the observable universe, beyond which we cannot directly see or measure. Challenging the idea of an infinite universe is the concept of cosmic inflation, a theory proposing that the universe underwent a period of rapid expansion in its earliest moments. Some models of inflation suggest that our observable universe might be just one of many bubble universes within a larger multiverse structure, potentially finite in extent. Additionally, the observed homogeneity and isotropy of the cosmos on large scales could be explained by a finite but extremely large universe, without the need for it to be infinite. Infinity in cosmology challenges our understanding of both space and time. In terms of space, the concept suggests that the universe might extend endlessly in all directions with no boundaries or edges. This idea of spatial infinity means that no matter how far we travel, we would never reach an end to the cosmos. When it comes to time, infinity raises questions about the age and future of the universe. Some theories propose that time stretches infinitely into the past, with no definitive beginning. Others suggest that time might continue forever into the future, with the universe expanding eternally. However, these concepts of infinity in cosmology are not without controversy. The observable universe, which is the part we can see and measure, is finite due to the limited speed of light and the age of the universe. Beyond this observable limit, the nature of space and time remains a subject of intense scientific debate and exploration. The idea of infinity in cosmology also intersects with theories about multiple universes and the potential cyclical nature of cosmic existence. These concepts push the boundaries of our understanding and highlight the ongoing quest to unravel the fundamental nature of reality. The concept of an infinite universe raises fascinating questions about the nature of reality and our place within it. While the idea of infinite copies of Earth and its inhabitants is intriguing, it's important to understand that an infinite universe doesn't necessarily guarantee infinite repetitions of everything. The observable universe, which is the part we can see and measure, is finite. However, many cosmologists theorize that the universe might extend far beyond what we can observe, potentially infinitely. If this is true, and if matter is distributed relatively evenly throughout this infinite space, then statistically, given enough space and time, arrangements of matter similar to our Earth could occur multiple times. However, exact copies are extremely unlikely. The sheer number of variables involved in the formation of a planet, the evolution of life, and the development of complex organisms and civilizations makes an exact duplicate improbable, even in an infinite universe. Small variations in initial conditions could lead to vastly different outcomes over time. Moreover, our current understanding of quantum mechanics suggests that true, identical copies might be impossible due to the inherent uncertainty and probabilistic nature of subatomic particles. So while an infinite universe might contain countless Earth-like planets with similar life forms, each would likely have unique characteristics and histories. Infinite universe theories approach the question of the universe's origin from a fundamentally different perspective than finite universe models. These theories propose that our universe has always existed and will continue to exist indefinitely, without a definitive beginning or end. This concept challenges the need for a singular origin event, such as the Big Bang, by suggesting that the universe is in a constant state of creation and destruction. One prominent infinite universe theory is the steady-state model, which posits that the universe maintains a constant average density as it expands. New matter is continuously created to fill the growing space, ensuring the universe remains essentially unchanged over time. While this theory has fallen out of favor due to observational evidence supporting the Big Bang, it demonstrates how infinite models attempt to sidestep the origin question. More recent infinite universe theories, such as the cyclic model, propose that our universe undergoes endless cycles of expansion and contraction. In this scenario, each cycle ends with a big crunch, followed by a new Big Bang, effectively eliminating the need for an absolute beginning. These models often incorporate concepts from string theory and the idea of higher dimensions to explain the mechanics of this perpetual cycle. Some versions of the multiverse theory also present an infinite perspective on the universe's origin. They suggest that our observable universe is just one of countless universes, each with its own set of physical laws and constants. In this view, universes are continually spawning new universes, creating an endless cosmic landscape without a definitive starting point. An infinite universe presents several mind-bending paradoxes that challenge our understanding of reality. One such paradox is the idea that in an infinite universe, everything that can happen will happen, not just once, but an infinite number of times. This means there would be an infinite number of Earths, each slightly different from the next, with an infinite number of variations of you reading this exact sentence. Another paradox arises from the concept of infinity itself. In an infinite universe, there would be an infinite amount of matter and energy. However, this conflicts with our observations of the universe, which show a relatively even distribution of matter on large scales. If the universe were truly infinite, we might expect to see infinitely dense regions or infinitely large structures which we do not observe. The thermal equilibrium paradox also emerges in an infinite universe. Given infinite time and space, the universe should reach a state of maximum entropy where energy is evenly distributed. This would result in a universe without structure or life, often called the heat death of the universe. Yet, we observe a universe full of structure and far from equilibrium. Lastly, an infinite universe raises questions about the nature of uniqueness and identity. If there are infinite copies of everything, including ourselves, what does it mean to be an individual? These paradoxes highlight the challenges in conceptualizing and understanding the true nature of our universe, pushing the boundaries of our scientific and philosophical thinking. Cosmic inflation provides a compelling explanation for the uniformity and flatness of our observable universe. This theory suggests that in the earliest moments after the Big Bang, the universe underwent a period of exponential expansion, stretching space itself faster than the speed of light. This rapid growth smoothed out any initial irregularities and expanded the universe to an enormous size in a fraction of a second. The connection between cosmic inflation and the possibility of an infinite universe lies in the nature of this expansion. According to some models of inflation, the process may not have stopped everywhere at once. Instead, inflation might have ended in some regions while continuing in others, leading to the creation of multiple universes or regions of space-time that are causally disconnected from our own. This scenario, known as eternal inflation, proposes that new universes or bubble universes are constantly forming within an ever-expanding cosmic framework. If true, this would imply that our observable universe is just one finite region within a much larger, potentially infinite multiverse. However, it is important to note that while the theory of cosmic inflation is well supported by observational evidence, the concept of an infinite universe or multiverse remains speculative. The limits of our observable universe constrain our ability to directly test these ideas, leaving them as intriguing possibilities at the frontier of cosmological research. Cosmic inflation is a theory that describes the exponential expansion of the early universe in the first fraction of a second after the Big Bang. This rapid growth caused the universe to expand faster than the speed of light, stretching space itself to an enormous size in an incredibly brief moment. The concept of inflation helps explain several observed features of our universe, including its uniformity on large scales and the nearly flat geometry of space. It also provides a mechanism for the formation of cosmic structures like galaxies and galaxy clusters. Inflation's connection to the multiverse comes from the idea that the process might not have stopped everywhere at once. In some regions, inflation could have continued, creating new, expanding bubbles of space-time. Each of these bubbles could potentially become a separate universe with its own physical laws and properties. This scenario, known as eternal inflation, suggests that our universe might be just one of many in a vast multiverse. Each universe in this multiverse would be causally disconnected from the others, existing as its own separate realm. While the multiverse concept remains speculative, it emerges naturally from some models of cosmic inflation, linking these two profound ideas in modern cosmology. Eternal inflation proposes a fascinating mechanism for the creation of multiple universes. This theory suggests that our universe began as a tiny region of space that underwent rapid expansion, known as cosmic inflation. However, the key idea of eternal inflation is that this process never truly ends. As inflation continues, certain areas of space stop inflating and form bubble universes, much like our own. These bubbles contain regions where inflation has ceased, allowing matter and energy to coalesce into galaxies and stars. Meanwhile, the space between these bubbles continues to expand at an exponential rate, creating more room for additional bubble universes to form. This ongoing process leads to the creation of a vast multiverse, with new universes constantly emerging within the ever-expanding inflationary space. Each of these bubble universes may have its own unique set of physical laws and constants, potentially differing from our own in significant ways. The eternal nature of this inflation means that the multiverse as a whole is endless, continuously giving birth to new universes across an infinite expanse of space and time. This concept challenges our understanding of the cosmos and opens up mind-boggling possibilities for the nature of reality beyond our observable universe. The bubble universe model is a fascinating concept within inflationary theory that suggests our universe might be just one of many. This idea proposes that during the rapid expansion of the early universe, known as cosmic inflation, different regions of space stopped inflating at different times. These regions where inflation ended became separate universes, each with its own physical laws and properties. Imagine a vast, expanding sea of space-time foam. In this foam, bubbles form and grow rapidly. Each bubble represents a universe coming into existence, expanding at an incredible rate. Our universe would be one such bubble, but according to this model, there could be countless others. These bubble universes might have different fundamental constants, different types of matter, or even different dimensions. Some could be similar to ours, while others might be utterly alien and incomprehensible by our standards. The space between these bubbles continues to inflate, keeping them eternally separated. This model offers a potential explanation for the fine-tuning of our universe. Instead of our universe being uniquely suited for life by chance or design, it suggests we simply exist in one of the countless bubbles where conditions happen to be right for our form of life to emerge. Other bubbles might harbor different forms of life or no life at all, depending on their particular properties. The concept of a multiverse suggests that our universe may be one of many, each potentially governed by its own set of physical laws. In different regions of the multiverse, fundamental constants and forces could vary, leading to dramatically different realities. For instance, in some universes, the strength of gravity might be much greater, causing matter to clump together more rapidly and form dense, short-lived worlds. In others, the electromagnetic force could be weaker, altering the behavior of atoms and the formation of complex molecules. The cosmological constant, which influences the expansion rate of a universe, might differ across the multiverse. Some universes could expand too quickly for stars and galaxies to form, while others might collapse back in on themselves before life has a chance to emerge. Even the number of dimensions could vary. While we experience 3 spatial dimensions and 1 of time, other universes might have additional dimensions, altering the very fabric of reality in ways we can scarcely imagine. These differences in physical laws would create a vast tapestry of diverse cosmic environments, each with its own unique properties and possibilities. The landscape in string theory refers to the vast array of possible universes predicted by the theory. String theory, a candidate for a unified theory of physics, suggests that our universe is just one of an enormous number of potential universes, each with its own unique set of physical laws and constants. This landscape is incredibly diverse, containing an estimated 10 to the power of 500 distinct possible universes. Each of these universes represents a different solution to the equations of string theory, with varying physical properties such as the number of dimensions, the types of particles, and the strengths of fundamental forces. The concept of the landscape directly connects to the idea of the multiverse. In this context, the multiverse is the collection of all these possible universes predicted by string theory. Each universe within the multiverse occupies a different point in the landscape with its own unique characteristics and laws of physics. This vast landscape of possibilities raises intriguing questions about our own universe. It suggests that the specific properties of our universe, which allow for the existence of complex structures like galaxies, stars, and life, might be just one configuration among countless others. This perspective has profound implications for our understanding of the cosmos and our place within it, challenging us to consider why our universe has the particular characteristics it does among the multitude of possibilities in the string theory landscape. The anthropic principle and multiverse theories intertwine in fascinating ways, offering potential explanations for our universe's seemingly perfect conditions for life. Multiverse theories propose the existence of numerous universes beyond our own, each with potentially different physical laws and constants. This vast array of universes provides a framework within which the anthropic principle becomes particularly relevant. The anthropic principle suggests that the observable properties of our universe must be compatible with the existence of conscious life that can observe it. In the context of multiverse theories, this principle takes on new significance. Among the countless universes that might exist, we inevitably find ourselves in one that allows for our existence. This does not mean our universe is special or designed for us, but rather that we could only exist in a universe with the right conditions. Multiverse theories offer a potential solution to the fine-tuning problem, which questions why our universe appears so precisely calibrated for life. Instead of requiring a single universe to be inexplicably perfect, multiverse theories propose that out of an enormous number of universes, some will naturally have the right conditions for life. We simply happen to inhabit one of these life-friendly universes. This connection between the anthropic principle and multiverse theories shifts our perspective on cosmic coincidences. Rather than viewing our universe as uniquely designed, we can understand it as one of many possibilities, where the conditions aligned just right for life to emerge and for us to ponder these very questions. Inflationary multiverse theories have faced several significant criticisms from within the scientific community. One primary concern is the lack of direct observational evidence. Critics argue that since other universes are, by definition, outside our observable realm, these theories remain speculative and difficult to test empirically. Another criticism revolves around the concept of falsifiability. Some scientists contend that if a theory can explain any possible observation, it loses its predictive power and scientific value. This critique suggests that multiverse theories might be unfalsifiable, potentially placing them outside the realm of testable science. Critics also point out the potential for infinite regress in multiverse explanations. If our universe is part of a larger multiverse, what caused or created the multiverse itself? This leads to questions about the ultimate origin of existence, which some argue the multiverse concept does not adequately address. Lastly, there are concerns about the application of probability theory to multiverse scenarios. Some scientists question whether it is valid to apply probabilistic reasoning to the entire cosmos, especially when we only have one observable universe to study. This criticism challenges the statistical foundations upon which some multiverse arguments are built. Testing predictions made by inflationary multiverse models present significant challenges due to the vast scales and energies involved. However, scientists have proposed several potential methods to gather evidence that could support or refute these theories. One approach involves searching for signatures of cosmic bubble collisions in the cosmic microwave background radiation. If our universe collided with another universe during its early expansion, it might have left subtle patterns in the temperature and polarization of this ancient light. Advanced telescopes and sophisticated data analysis techniques are being used to scour the cosmic microwave background for these telltale signs. Another avenue of investigation focuses on the distribution of matter in the observable universe. Inflationary multiverse models predict certain statistical patterns in how galaxies and other large structures are arranged. By mapping the cosmos in ever greater detail, astronomers hope to uncover evidence that aligns with these predictions. Gravitational waves offer yet another potential window into the multiverse. Some theories suggest that the collision of universes or the rapid expansion during inflation could produce distinctive gravitational wave signals. Future gravitational wave detectors, both on Earth and in space, might be sensitive enough to detect these faint echoes from the birth of universes. Brain cosmology is a fascinating concept in theoretical physics that expands our understanding of the universe beyond the traditional 4 dimensions of space and time. This theory proposes that our observable universe is actually a 3-dimensional membrane called a brain, floating within a higher dimensional space known as the bulk. In this model, gravity is the only force that can move freely between different branes, while other fundamental forces like electromagnetism are confined to specific branes. This could explain why gravity appears much weaker than the other forces in our universe, as its effects might be spread across multiple dimensions. Brain cosmology offers potential solutions to long-standing puzzles in physics, such as the hierarchy problem, which questions why gravity is so much weaker than the other fundamental forces. It also provides alternative explanations for the origin and evolution of our universe, suggesting that the Big Bang might have been caused by the collision of 2 branes. This theory opens up exciting possibilities for understanding parallel universes and the nature of dark matter and dark energy. While brain cosmology remains highly speculative and lacks experimental evidence, it continues to inspire physicists to explore new ways of thinking about the structure and origins of our universe. Brain theory offers a radical reimagining of the universe's structure, expanding our cosmic perspective beyond the familiar 4 dimensions of space and time. This concept, rooted in string theory, proposes that our universe exists as a 3-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. In this model, our universe is just one of many branes, each potentially harboring its own set of physical laws and fundamental forces. These branes might be stacked parallel to each other, separated by incredibly tiny distances in the extra dimensions we cannot directly perceive. The bulk itself could contain any number of dimensions beyond the four we experience. Gravity, unlike other fundamental forces, is theorized to operate across the entire bulk. This could explain why gravity appears so weak compared to other forces in our universe, as its effects might be spread across multiple dimensions. Brane theory also suggests that the collision or interaction of branes could be responsible for cosmic events like the Big Bang. While brane theory remains highly speculative and lacks experimental evidence, it attempts to unify quantum mechanics and gravity, addressing fundamental questions about the nature of space, time, and the origins of our universe. It challenges us to consider that what we perceive as reality might be just a slice of a much grander, multi-dimensional cosmos. In brane cosmology, the bulk refers to a higher dimensional space that encompasses our familiar four-dimensional universe. This concept emerges from string theory and M theory, which propose that our universe might be a three-dimensional membrane, or brane, floating within a larger multi-dimensional space. The bulk is often visualized as a vast, empty expanse that extends beyond the confines of our observable universe. It serves as the backdrop against which our universe and potentially other universes exist. This higher dimensional space is thought to have at least one more spatial dimension than our own universe, allowing for the possibility of parallel universes or other exotic phenomena. One of the intriguing aspects of the bulk is its potential to solve certain cosmological puzzles. For instance, it might explain the weakness of gravity compared to other fundamental forces, as gravity could be leaking into the bulk. Additionally, the existence of the bulk could account for dark matter and dark energy, as these mysterious components might be manifestations of how our brain interacts with the higher dimensional space. While the concept of the bulk remains largely theoretical, it has sparked numerous research avenues in theoretical physics and cosmology. Scientists continue to explore ways to test these ideas and search for observable consequences of living in a universe that might be just one part of a much larger, multidimensional reality. Brane collisions represent a fascinating concept in theoretical physics, offering a potential explanation for the creation of new universes. In this model, our universe exists as a three-dimensional membrane, or brane, floating in a higher dimensional space. Other branes may exist in this same space, and occasionally these branes might collide with one another. When two branes collide, the enormous energy released could spark the formation of a new universe. This process is somewhat analogous to the Big Bang theory, but instead of emerging from a singularity, the new universe would be born from the interaction between two existing cosmic structures. The collision would release an immense amount of energy, potentially creating matter, space, and time as we know them. This idea stems from string theory and M theory, which propose the existence of extra dimensions beyond the four we can observe. These theories suggest that gravity, unlike other fundamental forces, can leak between branes, explaining why gravity appears weaker than the other forces in our universe. While brane collisions remain a highly speculative concept, they offer an intriguing alternative to traditional cosmological models. If true, this would imply that our universe might be just one of many in a vast multiverse, each created by cosmic collisions on an unimaginable scale. However, detecting evidence of other branes or collisions remains a significant challenge for modern physics. The ekpyrotic universe model offers an alternative explanation for the origin and evolution of our cosmos. This theory proposes that our universe began not with a sudden expansion or Big Bang, but through the collision of two vast, flat membranes or branes in a higher dimensional space. In this scenario, these branes exist in a realm with more dimensions than the three spatial dimensions we observe. They move through this higher dimensional space, occasionally colliding with each other. The energy released during one of these collisions is believed to have sparked the creation of our universe. Brane cosmology, which forms the foundation for the ekpyrotic model, suggests that our entire universe exists on a three-dimensional membrane within a higher dimensional bulk space. This concept stems from string theory, which posits that the fundamental constituents of the universe are tiny, vibrating strings of energy. The ekpyrotic model attempts to address some of the challenges faced by the traditional Big Bang theory. It offers explanations for the uniformity of the cosmic microwave background radiation and the flatness of space without requiring a period of rapid inflation. Instead, it proposes that these features arose from the nature of the brane collision and the subsequent evolution of the universe. Brane cosmology offers an intriguing approach to addressing the hierarchy problem in physics, which puzzles scientists due to the vast difference between the strength of gravity and the other fundamental forces. This theory proposes that our universe exists on a three-dimensional membrane, or brane, floating within a higher dimensional space called the bulk. In this model, gravity is not confined to our brane, but can spread out into the extra dimensions of the bulk. This spreading out, or dilution, of gravity could explain why it appears so weak in our three-dimensional world compared to the other forces. The other fundamental forces, in contrast, are thought to be confined to our brane, maintaining their full strength. The existence of extra dimensions in brane cosmology also suggests that the true scale of gravity might be much closer to that of the other forces than we observe. The apparent weakness of gravity in our world could be an illusion caused by its dispersion across these hidden dimensions. This concept provides a potential solution to the hierarchy problem without requiring the introduction of new particles or forces in our observable universe. Brane cosmology not only addresses the hierarchy problem, but also opens up new avenues for understanding other cosmological mysteries, such as the nature of dark matter and dark energy. While this theory remains speculative and requires further evidence, it represents an innovative attempt to unify our understanding of the fundamental forces that shape our universe. Brane cosmology theories propose that our universe exists on a multidimensional membrane, or brane, within a higher dimensional space. While these theories remain speculative, scientists have considered several potential observational signatures that could provide evidence for their validity. One intriguing possibility is the detection of gravitational waves with unexpected frequencies or amplitudes. According to brane theories, gravity might be able to propagate through extra dimensions, potentially leading to gravitational wave signals that deviate from the predictions of standard general relativity. Advanced gravitational wave detectors could potentially pick up these anomalous signals, offering a window into higher dimensions. Another avenue of investigation involves searching for slight variations in the strength of gravity over very large distances. Some brane models predict that the force of gravity might behave differently on cosmic scales compared to what we observe in our local environment. Precise measurements of galactic motions and the expansion of the universe could reveal these subtle deviations, providing support for brane cosmology. Cosmic microwave background radiation, the afterglow of the Big Bang, might also hold clues. Brane theories suggest that our universe could have collided with other branes in the past, potentially leaving observable imprints on this primordial radiation. Detailed analysis of the cosmic microwave background could uncover patterns or anomalies that align with predictions from brane cosmology, offering tantalizing evidence for these multidimensional models. Brane cosmology presents a radical departure from traditional Big Bang theory, offering a new perspective on the origin and structure of our universe. In this model, our universe exists as a three-dimensional membrane, or brane, floating within a higher dimensional space called the bulk. This contrasts sharply with the standard Big Bang model, which describes our universe as a singular four-dimensional space-time continuum. The key difference lies in how these models explain the beginning of the universe. Traditional Big Bang cosmology posits that the universe began as an infinitely dense singularity that rapidly expanded. Brain cosmology, however, suggests that our universe resulted from a collision between two brains in the higher dimensional bulk. This collision event replaces the singularity of the Big Bang, potentially resolving some of the mathematical issues associated with the traditional model. Brain cosmology also offers new explanations for some of the most puzzling aspects of our universe. For instance, it provides a potential solution to the hierarchy problem in physics, explaining why gravity appears so much weaker than the other fundamental forces. In this model, gravity can spread into the extra dimensions of the bulk, while the other forces remain confined to our brain. Furthermore, brain cosmology opens up intriguing possibilities, such as the existence of parallel universes on other brains within the bulk. This idea challenges our conventional understanding of the cosmos and pushes the boundaries of theoretical physics, offering a dramatically different vision of the universe compared to the traditional Big Bang model. A cyclic universe model proposes that the cosmos undergoes endless cycles of expansion and contraction. This concept challenges the idea of a single Big Bang origin, suggesting instead that our universe is just one in a series of universes that have existed before and will exist after our own. In this model, the universe expands from a hot, dense state, much like in the Big Bang theory. However, instead of expanding indefinitely, it eventually slows down and begins to contract. This contraction leads to what some scientists call a big crunch, where all matter and energy collapse back into a super-dense state. From this point, a new expansion begins, giving birth to a new universe. Proponents of cyclic models argue that this process could repeat indefinitely, with each cycle lasting trillions of years. Some versions of the theory suggest that each cycle produces slightly different physical laws or constants, potentially explaining why our universe seems finely tuned for life. While intriguing, cyclic universe models face several challenges. Scientists are still working to understand how the transition from contraction to expansion could occur without violating known physical laws. Additionally, current observations suggest our universe is expanding at an accelerating rate, which seems to contradict the eventual contraction required by most cyclic models. A cyclic universe model presents a fascinating alternative to the standard Big Bang theory. While the Big Bang proposes a singular beginning to our universe, the cyclic model suggests that our cosmos undergoes endless cycles of expansion and contraction. In this cyclical view, the universe expands from a hot, dense state, much like in the Big Bang model. However, instead of expanding indefinitely, it eventually slows down and begins to contract. This contraction leads to what some scientists call a big crunch, where all matter and energy collapse back into a super-dense state. From this point, a new cycle begins with another expansion phase. One key difference is the concept of time. The Big Bang model implies a definite starting point for our universe, often described as the beginning of time itself. In contrast, the cyclic model proposes no absolute beginning or end, just an eternal series of cycles. Another distinction lies in the fate of the universe. The standard model predicts several possible endpoints, such as eternal expansion or a big freeze. The cyclic model, however, envisions a perpetual rhythm of renewal and rebirth for the cosmos, offering a different perspective on the ultimate destiny of our universe. The Big Bounce theory offers an alternative perspective to the widely accepted Big Bang model of the universe's origin. This concept suggests that our universe undergoes a continuous cycle of expansion and contraction, rather than having a singular beginning. According to this theory, the universe expands until it reaches a maximum size, then begins to contract due to the force of gravity. As it shrinks, all matter and energy are compressed into an incredibly dense state. However, instead of collapsing into a singularity as proposed by some models, the universe reaches a point of maximum density and then bounces back, beginning a new phase of expansion. This process of expansion, contraction, and rebounding is thought to repeat indefinitely, creating a cyclical universe with no absolute beginning or end. Proponents of the Big Bounce theory argue that it addresses some of the challenges faced by the Big Bang model, such as the nature of the initial singularity and what might have existed before the Big Bang. While the Big Bounce theory is intriguing, it remains speculative and faces its own set of challenges. Scientists continue to debate and investigate various models of cosmic evolution, seeking to unravel the mysteries of our universe's origin and ultimate fate. The concept of a cyclic universe offers an intriguing solution to the perplexing question of what came before the Big Bang. In this model, our universe undergoes a continuous cycle of expansion, contraction, and rebirth, eliminating the need for a definitive beginning. According to the cyclic universe theory, our current universe is just one in an endless series of universes. Each cycle begins with a Big Bang, expands for billions of years, and then contracts back into a singularity, only to explode outward again in a new Big Bang. This process repeats indefinitely, with no true starting point. This model addresses the issue of what preceded the Big Bang by suggesting that there was always a previous universe. It proposes that time and space continue infinitely into the past and future, with each cycle lasting perhaps 1 trillion years. The cyclic nature of this concept aligns with patterns observed in nature and offers a potential explanation for the origin and fate of our cosmos. However, it is important to note that while the cyclic universe theory is compelling, it remains speculative. Scientists continue to debate its validity and search for observable evidence that could support or refute this model of cosmic evolution. Cyclic universe models propose that our universe undergoes endless cycles of expansion and contraction, rather than having a single beginning. This idea has intrigued cosmologists for decades, offering an alternative to the traditional Big Bang theory. One piece of evidence supporting cyclic models is the observed acceleration of cosmic expansion. This acceleration could eventually lead to a big rip, tearing apart all matter and resetting the universe for a new cycle. Additionally, some versions of string theory predict the existence of brains, multidimensional structures that could collide and trigger new cycles of universal expansion. However, cyclic models face significant challenges. The second law of thermodynamics suggests that entropy should increase with each cycle, making it difficult to explain how the universe resets to a low entropy state. Furthermore, observations of the cosmic microwave background radiation align closely with predictions from inflationary Big Bang models, leaving less room for cyclic alternatives. Current observational data neither conclusively proves nor disproves cyclic universe models. As our understanding of physics and our ability to observe the cosmos improve, we may gain more insight into whether our universe is a one-time event or part of an endless cosmic cycle. Cyclic models of the universe propose a fascinating alternative to the idea of a single Big Bang. These theories suggest that our universe undergoes a continuous cycle of expansion and contraction, with each cycle potentially lasting trillions of years. However, the concept of ever-increasing entropy and the arrow of time pose significant challenges to these models. Entropy, often described as the measure of disorder in a system, tends to increase over time according to the second law of thermodynamics. This law seems to conflict with the idea of a cyclic universe, as each cycle would theoretically start with higher entropy than the last. To address this issue, some cyclic models propose mechanisms to reset or reduce entropy between cycles. One approach suggests that the contraction phase of the cycle might somehow reverse the arrow of time, effectively undoing the increase in entropy. Another idea posits that the universe expands to such an extent that entropy becomes diluted across vast distances, essentially resetting the system for the next cycle. Some theories even propose that new, low-entropy regions emerge during the transition between cycles. Despite these creative solutions, the entropy problem remains a significant hurdle for cyclic models. Scientists continue to grapple with how to reconcile the apparent directionality of time and the increase of entropy with the cyclical nature proposed by these theories. The ongoing debate surrounding this issue highlights the complex interplay between cosmology, thermodynamics, and our understanding of time itself. Dark energy plays a crucial role in cyclic universe theories, acting as a driving force behind the expansion and contraction of the cosmos. In these models, our universe undergoes repeated cycles of expansion and collapse, rather than a single linear progression. As dark energy causes the universe to expand at an accelerating rate, it eventually leads to a state where matter becomes extremely diffuse. Some cyclic models propose that this expansion continues until the fabric of space itself begins to tear. This cosmic rip initiates a reversal, causing the universe to contract and eventually collapse back into a dense state similar to the conditions before the Big Bang. During the contraction phase, the immense gravitational forces overcome the repulsive effect of dark energy. This collapse leads to extreme conditions that spark another expansion, beginning the cycle anew. The precise mechanics of this transition remain a subject of intense study and debate among cosmologists. Cyclic universe theories incorporating dark energy offer an alternative to the idea of a single universe with a definitive beginning and end. They suggest that our current cosmic era might be just one of many in an endless cycle of rebirth and renewal, with dark energy serving as a key player in this cosmic dance. Cyclic universe models challenge our traditional view of cosmic history and the nature of reality beyond our observable universe. These theories propose that our universe undergoes a repeating cycle of expansion, contraction, and rebirth, rather than having a single definitive beginning or end. This concept dramatically alters our perspective on what might exist beyond our cosmic horizon. Instead of an infinite, static void or a multiverse of parallel universes, cyclic models suggest a succession of universes, each born from the remnants of its predecessor. Our current universe could be just one iteration in an endless series of cosmic cycles. Cyclic models also raise intriguing questions about the transfer of information or physical laws between cycles. Some theories propose that certain fundamental constants or large-scale structures might carry over from one universe to the next, potentially leaving subtle clues about previous cosmic epochs embedded in our own universe. Furthermore, these models challenge our understanding of time itself. If the universe repeats endlessly, the very concept of a beginning becomes meaningless, forcing us to reconsider our notions of causality and the arrow of time on a cosmic scale. This perspective could fundamentally reshape our approach to cosmology and our quest to understand the ultimate nature of reality. A white hole is a hypothetical cosmic object that acts as the opposite of a black hole. While black holes pull everything in, including light, white holes would theoretically push everything out, expelling matter and energy into space. This concept arises from mathematical solutions to Einstein's field equations of general relativity, which allow for the existence of such an entity. In theory, a white hole cannot be entered from the outside, making it a region of space-time that nothing can ever reach. It would appear as an intensely bright spot in space, constantly ejecting material and light. Some physicists speculate that white holes could be the other end of black holes, potentially forming a bridge between different regions of space or even different universes. However, it is important to note that white holes remain purely theoretical. No observational evidence supports their existence, and many scientists question whether they could exist in reality. The concept of white holes challenges our understanding of thermodynamics and the arrow of time, as they would essentially reverse the process of gravitational collapse. Despite their speculative nature, white holes continue to fascinate cosmologists and theoretical physicists. They represent an intriguing possibility in our quest to understand the fundamental nature of space, time, and the universe itself. White holes and black holes represent two fascinating extremes in the realm of theoretical astrophysics. While black holes are well-established cosmic phenomena, white holes remain purely theoretical, existing only in mathematical equations. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. They form when massive stars collapse or when galaxies collide. These cosmic behemoths continuously pull in matter and energy from their surroundings, growing ever more massive over time. White holes, in contrast, would be the exact opposite. If they existed, white holes would eject matter and light, making it impossible for anything to enter them. They would essentially be black holes in reverse, spewing out material instead of consuming it. Some theories suggest that white holes could be the other end of a black hole, connected by a theoretical tunnel in spacetime called a wormhole. However, unlike black holes, which we have observed indirectly through their effects on nearby stars and gas, there is no observational evidence for white holes. Their existence remains a topic of debate among physicists, with some arguing that they are mathematically possible but likely unstable in the real universe. The concept of white holes continues to intrigue scientists, pushing the boundaries of our understanding of space, time, and the fundamental laws of physics. White holes, the theoretical opposite of black holes, have captivated scientists and space enthusiasts alike. While black holes pull everything in, white holes would theoretically expel matter and light, making them impossible to enter. Some researchers have proposed that white holes could indeed be the birthplaces of new universes. This concept ties into the idea of a multiverse, where our universe is just one of many. The theory suggests that the immense gravitational forces and extreme conditions inside a black hole might lead to the formation of a white hole in another realm. This white hole could then explosively eject matter and energy, potentially giving rise to a new universe with its own physical laws and constants. However, it is crucial to note that white holes remain purely theoretical. No observational evidence supports their existence, and many scientists question whether they could exist within the framework of our current understanding of physics. The mathematics describing white holes work on paper, but the conditions required for their formation might be impossible to achieve in reality. Despite these challenges, the concept of white holes as universe generators continues to intrigue cosmologists. It offers a potential explanation for the origin of our own universe and provides a mechanism for the creation of multiple universes. As our understanding of physics and the cosmos evolves, we may gain new insights into these enigmatic theoretical objects and their possible role in the grand tapestry of existence. The theory of universe creation through black hole collapse proposes an intriguing mechanism for the birth of new universes. This concept suggests that when a black hole forms in our universe, the extreme conditions inside it could lead to the creation of an entirely new universe. As a black hole collapses, the matter within it becomes incredibly dense, and the laws of physics as we know them begin to break down. Some scientists speculate that this process could trigger a sort of rebound effect, causing the formation of a new, expanding region of space-time. This new region would be cut off from our own universe, essentially becoming a separate cosmos with its own physical laws and properties. This theory draws parallels between the properties of black holes and the characteristics of our own universe. Both involve extreme density and the apparent emergence of space-time from a singular point. The idea also aligns with concepts from string theory and other models of quantum gravity, which suggest the possibility of multiple universes or dimensions. While this theory remains highly speculative and lacks observational evidence, it offers a fascinating perspective on the potential cyclical nature of universe creation. It suggests that our own universe might be the result of a black hole collapse in a parent universe, and that black holes in our cosmos could be giving birth to new universes, continuing an endless cycle of cosmic creation. The information paradox of black holes has long puzzled physicists, but white holes offer an intriguing potential solution. Black holes, as we understand them, consume everything that crosses their event horizon, including information. This seems to violate a fundamental principle of quantum mechanics, which states that information cannot be destroyed. White holes, theoretical cousins to black holes, might provide an answer. While black holes only allow matter and energy to enter, never to escape, white holes would do the opposite. They would only allow matter and energy to exit, never to enter. Some theories propose that black holes and white holes could be connected, forming a bridge across space and time. In this scenario, everything that falls into a black hole could potentially emerge from a white hole, preserving the information that seemed lost. This connection, sometimes called an Einstein-Rosen bridge or wormhole, could ensure that information is not destroyed but rather transferred to another region of spacetime. However, it is important to note that white holes remain purely theoretical. While they are mathematically possible solutions to Einstein's field equations, we have no observational evidence for their existence. The concept nonetheless provides a fascinating avenue for exploring solutions to the black hole information paradox and pushes our understanding of the universe to new frontiers. Detecting white holes, the theoretical counterparts to black holes, poses significant challenges for astronomers. Unlike black holes, which have been indirectly observed through their effects on nearby matter and space, white holes remain purely hypothetical. However, scientists have proposed several potential observational signatures that could hint at their existence. One possible indicator might be the detection of unusual gravitational wave patterns. If a white hole were to form and then quickly collapse, it could produce a distinctive gravitational wave signal different from those generated by merging black holes or neutron stars. Gravitational wave detectors like LIGO and Virgo could potentially capture such unique signatures. Another potential sign could be the observation of matter seemingly appearing from nowhere in space. White holes, by definition, would eject matter and light rather than consume it. Astronomers might detect sudden bursts of energy or matter in regions of space where no obvious source is present. This could manifest as unexplained gamma-ray bursts or the appearance of new, highly energetic objects in previously empty areas of the cosmos. Some researchers have also suggested that certain gamma-ray bursts or ultra-high-energy cosmic rays might originate from white holes. These extremely energetic phenomena currently lack fully explained sources, and white holes could potentially provide the enormous energy required to produce them. However, it is crucial to note that while these observations might be consistent with white hole behavior, they do not conclusively prove their existence, and other explanations may be possible. White holes and wormholes are both fascinating theoretical concepts in cosmology, each pushing the boundaries of our understanding of space and time. While black holes are regions from which nothing can escape, white holes are their hypothetical opposites, regions that nothing can enter but from which matter and light can escape. Wormholes, on the other hand, are theoretical tunnels through space-time that could potentially connect two distant points in the universe. The connection between white holes and wormholes becomes apparent when we consider the mathematics of general relativity. Some solutions to Einstein's field equations suggest that a white hole could form the other end of a wormhole, with a black hole at one entrance and a white hole at the exit. This configuration is sometimes called an Einstein-Rosen bridge. In this theoretical scenario, matter and light that falls into a black hole would emerge from a white hole, potentially in another region of space or even another universe. However, it is important to note that while these mathematical solutions exist, we have no observational evidence for either white holes or traversable wormholes in our universe. The relationship between white holes and wormholes highlights the interconnected nature of these extreme space-time geometries. Both concepts challenge our understanding of causality and the fundamental structure of the universe, prompting scientists to explore the limits of general relativity and quantum mechanics in search of a more complete picture of cosmic phenomena. The concept of our universe originating from a white hole in another universe is a fascinating idea that has captured the imagination of cosmologists and theoretical physicists. White holes are hypothetical cosmic regions that are essentially the opposite of black holes. While black holes pull everything in, white holes would theoretically eject matter and light, making it impossible to enter them. Some scientists have proposed that the Big Bang, the event believed to have marked the beginning of our universe, could have been the result of a white hole explosion. This idea suggests that our entire cosmos might have burst forth from a singularity in another universe, similar to how matter and energy cannot escape a black hole in our universe. This concept ties into the broader theory of a multiverse, where multiple universes exist alongside or nested within each other. In this scenario, each universe could be connected through cosmic bridges like wormholes, with black holes in one universe potentially linked to white holes in another. However, it is crucial to note that white holes remain purely theoretical. They have never been observed, and many scientists question whether they can exist within the laws of physics as we understand them. While the idea of our universe originating from a white hole is intriguing, it remains speculative and lacks observational evidence to support it. The holographic principle is a fascinating concept in theoretical physics that suggests our three-dimensional reality might be an illusion. This principle proposes that all the information contained within a region of space can be described on a two-dimensional boundary of that region. To understand this better, think of a hologram. A flat, two-dimensional surface can create the illusion of a three-dimensional image. The holographic principle takes this idea to a cosmic scale, suggesting that our entire universe might function in a similar way. All the information about our three-dimensional world, including gravity, could potentially be encoded on a distant, two-dimensional surface. This principle arose from studies of black holes, where scientists discovered that the information about everything that falls into a black hole appears to be stored on its event horizon, the black hole's boundary. This led to the idea that perhaps our entire universe operates on a similar principle. The holographic principle challenges our perception of reality and space. It suggests that what we experience as three-dimensional might be a projection of information stored on a two-dimensional surface, much like a hologram. This concept has profound implications for our understanding of quantum gravity, the nature of space-time, and the fundamental structure of the universe. The holographic universe theory proposes a radical reimagining of reality as we know it. This concept suggests that our three-dimensional world might be a projection of information stored on a two-dimensional surface, similar to how a hologram creates the illusion of depth from a flat image. At its core, the theory draws parallels between the way information is encoded in a hologram and how our universe might function. Just as a small piece of a hologram contains information about the entire image, this theory posits that each region of space contains information about the entire universe. This idea emerged from studies of black holes and string theory. Scientists discovered that the information about objects falling into a black hole could be completely described by the surface area of the event horizon, not its volume. This led to the notion that perhaps our entire universe operates on a similar principle. If true, the holographic universe theory could help reconcile quantum mechanics with Einstein's theory of gravity, two fundamental pillars of physics that have long resisted unification. It challenges our perception of reality and suggests that the universe we experience might be a complex projection of more fundamental processes occurring on a distant, two-dimensional surface. The holographic principle is a fascinating concept in theoretical physics that suggests our three-dimensional universe might be a projection of information stored on a two-dimensional surface. This idea draws support from several lines of evidence and theoretical work. One key piece of evidence comes from the study of black holes. Physicists discovered that the information content of a black hole is proportional to its surface area, not its volume. This unexpected relationship hinted at a possible holographic nature of space and time, extending beyond just black holes to potentially the entire universe. String theory, a prominent framework for understanding fundamental physics, provides additional support for the holographic principle. In certain string theory models, researchers found mathematical equivalences between theories describing gravity in a space with a particular geometry and quantum theories without gravity in a lower dimensional space. This correspondence, known as the AD-S-CFT correspondence, strengthens the case for a holographic universe. Recent experiments have also lent credence to this idea. Scientists have used quantum simulations to model a holographic universe, finding that these models can accurately describe certain quantum systems. While these experiments do not prove our universe is holographic, they demonstrate that holographic principles can apply to real-world physics, adding weight to the possibility of a holographic cosmos. The holographic principle and string theory are two fascinating concepts in theoretical physics that have become increasingly intertwined. The holographic principle suggests that all the information contained within a region of space can be described on its boundary. This idea, originally proposed in the context of black holes, has profound implications for our understanding of the universe. String theory, on the other hand, is a theoretical framework that attempts to unify all fundamental forces and particles. It proposes that the basic constituents of the universe are not point-like particles, but tiny, vibrating strings. These strings exist in multiple dimensions, most of which are too small for us to perceive directly. The connection between these two ideas comes from the realization that certain string theories can be equivalent to theories of gravity in a space with one fewer dimension. This correspondence, known as the AD-S-CFT correspondence, provides a concrete realization of the holographic principle within the framework of string theory. This relationship has led to new insights in both fields. It allows physicists to study complex gravitational systems by analyzing simpler quantum systems on their boundaries. Conversely, it provides new tools for understanding quantum systems by relating them to gravitational theories. This unexpected connection between string theory and the holographic principle continues to be a rich area of research, potentially offering a path towards a deeper understanding of the fundamental nature of space, time, and information in our universe. The concept of a holographic universe challenges our traditional understanding of dimensions and spatial reality. In this model, our three-dimensional world might be a projection from a two-dimensional surface, much like a hologram. This idea stems from the holographic principle in string theory and has profound implications for how we perceive space, time, and the fundamental nature of our reality. If our universe is indeed holographic, it suggests that the information contained within any region of space can be described by information on the surface that surrounds it. This would mean that the volume of space is illusory and the true nature of reality is encoded on a distant, two-dimensional surface. Such a revelation would force us to reconsider our notions of up, down, left, and right, as these concepts might be mere projections of more fundamental information. Furthermore, a holographic universe implies that our perception of depth and dimensionality might be an emergent property, rather than a fundamental aspect of reality. This could explain why we struggle to reconcile quantum mechanics, which often deals with two-dimensional systems, with our three-dimensional classical world. It might also provide new avenues for understanding phenomena like quantum entanglement and the nature of black holes. The holographic principle also raises questions about the limits of information storage in our universe. If all the information in a volume can be described by its surface area, it suggests a fundamental limit to the amount of information that can exist in any given region of space. This has far-reaching consequences for our understanding of physics, computation, and even the nature of consciousness itself. The idea of a holographic universe challenges our fundamental understanding of reality and space. If our universe is indeed holographic, it suggests that all the information contained within our three-dimensional world might actually be encoded on a two-dimensional surface, much like a hologram. This concept dramatically alters our perception of what lies beyond our observable universe. In a holographic universe, the boundary or edge of our cosmos could be viewed as a sort of cosmic horizon, containing all the information needed to describe everything within it. This would mean that what we perceive as depth, or a third dimension, might be an illusion arising from the way information is organized on this two-dimensional boundary. This perspective raises intriguing questions about the nature of what lies beyond our universe. If our reality is a projection from a two-dimensional surface, then the concept of beyond takes on new meaning. There might not be a physical beyond in the way we typically imagine it. Instead, what lies beyond could be related to the information encoded on this cosmic horizon, or perhaps other two-dimensional surfaces encoding different universes. The holographic principle also connects to string theory and quantum gravity, suggesting that our understanding of space, time, and the fabric of reality at the smallest scales might be fundamentally linked to the largest scales of the cosmos. This interconnectedness implies that exploring what lies beyond our universe might require us to look not outward, but inward, to the very nature of information and reality itself. Scientists are actively exploring the holographic principle through various ingenious experiments. One notable effort is the holometer experiment at Fermilab, which uses powerful lasers to detect potential quantum jitter in spacetime. This experiment aims to measure incredibly small fluctuations that could indicate a fundamental graininess of space, supporting the idea that our three-dimensional reality might be a projection of information stored on a two-dimensional surface. Another approach involves studying the cosmic microwave background, the afterglow of the Big Bang. Researchers analyze its patterns for evidence of holographic noise, which could suggest that the early universe encoded information holographically. Additionally, some scientists are investigating black holes, as these extreme objects play a crucial role in holographic theories. They study the behavior of information near the event horizon, seeking clues about how three-dimensional information might be stored on a two-dimensional surface. Quantum entanglement experiments also contribute to testing the holographic principle. By examining how quantum information is distributed and connected across space, scientists hope to uncover evidence of holographic encoding in the fabric of the universe. These experiments push the boundaries of our understanding of quantum mechanics and gravity, potentially revealing deep connections between these fundamental forces. As technology advances, researchers continue to devise new ways to test the holographic principle. From tabletop experiments to space-based observatories, scientists are leaving no stone unturned in their quest to determine whether our universe truly operates like a vast hologram, with all its complexity emerging from information encoded on a lower dimensional surface. The holographic universe theory presents a radical reimagining of our reality, suggesting that the world we perceive as three-dimensional might actually be a projection from a two-dimensional surface. This concept challenges our most fundamental understanding of space and time, proposing that the universe operates much like a hologram. At its core, this theory posits that all the information about our universe is encoded on a distant, two-dimensional surface, similar to how a credit card hologram contains three-dimensional information on a flat plastic card. This means that everything we experience, from the chair you sit on to the farthest galaxies, could be projections from this cosmic two-dimensional boundary. This theory has profound implications for our understanding of black holes, quantum mechanics, and even the nature of consciousness. It suggests that the apparent solidity of our world might be an illusion, and that reality at its most fundamental level could be composed of information rather than matter and energy as we traditionally conceive them. If true, the holographic principle would require us to completely re-evaluate our place in the cosmos. It challenges us to consider that our perceptions of depth, time, and physical laws might be emergent properties of a more fundamental reality we cannot directly observe. This mind-bending concept continues to inspire physicists and philosophers alike as they grapple with the true nature of our universe. Quantum fluctuations are tiny, rapid changes in energy that occur constantly at the smallest scales of the universe. These fluctuations are a fundamental aspect of quantum mechanics, the branch of physics that describes the behavior of matter and energy at the atomic and subatomic levels. In the quantum world, the principle of uncertainty reigns supreme. This principle states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. As a result, even in seemingly empty space, particles can spontaneously appear and disappear, borrowing energy from the vacuum for incredibly brief moments. These fleeting bursts of energy and matter are quantum fluctuations. They happen so quickly and on such a small scale that they are impossible to directly observe. However, their effects can be measured and have profound implications for our understanding of the universe. Quantum fluctuations played a crucial role in the early universe, seeding the tiny irregularities that eventually grew into the large-scale structures we see today, such as galaxies and galaxy clusters. They continue to influence the universe at the quantum level, shaping the behavior of particles and fields in ways that challenge our classical intuitions about reality. Quantum fluctuations are fundamental to our understanding of how universes might come into existence. At the smallest scales of reality, the quantum realm behaves in ways that defy our everyday logic. In this bizarre world, particles can appear and disappear spontaneously, emerging from and returning to the quantum vacuum. These fleeting quantum fluctuations usually balance out over time, but under certain conditions, they can have profound consequences. Some theories suggest that an exceptionally large quantum fluctuation could lead to a rapid expansion of space, creating a bubble of new spacetime. This process, known as quantum nucleation, might be the seed from which entire universes grow. In the context of cosmic inflation theory, these quantum fluctuations could be amplified to cosmic scales. As the early universe underwent a period of exponential expansion, tiny quantum variations could have been stretched and magnified, eventually becoming the large-scale structures we observe today, such as galaxies and galaxy clusters. The concept of quantum fluctuations creating universes aligns with some multiverse theories. It suggests that our universe might be just one of many, each born from its own quantum fluctuation in a vast, eternal sea of quantum possibilities. This idea challenges our notions of cosmic origins and hints at a reality far more complex and diverse than we once imagined. Quantum foam is a concept in theoretical physics that describes the fundamental nature of spacetime at incredibly tiny scales. At these minuscule levels, far smaller than atoms, spacetime is thought to be constantly fluctuating and bubbling with energy, much like the froth on the surface of a turbulent ocean. This foam-like structure arises from the principles of quantum mechanics, which govern the behavior of particles and energy at the smallest scales. In quantum foam, virtual particles and antiparticles are constantly popping into and out of existence, creating a seething, ever-changing landscape of energy. The idea of quantum foam relates to universe creation in fascinating ways. Some theories suggest that our entire universe may have emerged from a particularly large fluctuation in this quantum foam. This concept aligns with certain models of cosmic inflation, where the universe rapidly expanded from a tiny point to its current vast size in the earliest moments after the Big Bang. Furthermore, quantum foam might explain how new universes could potentially form. In this view, tiny bubbles of spacetime could expand rapidly, giving birth to entirely new cosmic realms. This idea forms the basis for some multiverse theories, suggesting our universe might be just one of many that have sprouted from the underlying quantum foam of reality. Quantum fluctuations and the uncertainty principle are intimately connected, both arising from the fundamental nature of quantum mechanics. The uncertainty principle, formulated by Werner Heisenberg, states that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with infinite precision. This inherent uncertainty in quantum systems gives rise to quantum fluctuations. These fluctuations are rapid, temporary changes in the amount of energy at a specific point in space. They occur because the uncertainty principle allows energy to briefly violate conservation laws, popping in and out of existence on incredibly short timescales. This constant flux of energy at the quantum level creates a sort of quantum foam, where particles and antiparticles continuously appear and annihilate each other. The relationship between quantum fluctuations and the uncertainty principle is not just theoretical, but has observable consequences. For instance, these fluctuations contribute to the Casimir effect, where two uncharged metal plates in a vacuum experience a small attractive force. This force arises from the difference in quantum fluctuations between the space inside and outside the plates. Understanding quantum fluctuations and the uncertainty principle has far-reaching implications, from explaining the behavior of particles in the early universe to potentially harnessing quantum effects for advanced technologies. These concepts challenge our classical intuitions about the nature of reality, revealing a quantum world that is inherently probabilistic and uncertain at its smallest scales. The idea that our universe might have originated from a quantum fluctuation is a fascinating concept in modern cosmology. Quantum fluctuations are tiny, random changes in energy that occur at the subatomic level due to the inherent uncertainty in quantum mechanics. These fluctuations happen constantly, even in what we consider empty space. Some theoretical physicists propose that a particularly large quantum fluctuation could have provided the initial energy needed to trigger the rapid expansion of space known as cosmic inflation. This expansion would have then led to the Big Bang, effectively giving birth to our universe. This theory aligns with our understanding of quantum mechanics and offers a potential explanation for how something could arise from seemingly nothing. However, it is important to note that this concept pushes the boundaries of our current scientific knowledge. We cannot directly observe or test events that occurred before the Big Bang, making it challenging to confirm or refute this hypothesis. While the quantum fluctuation origin theory is intriguing, it remains one of several competing ideas about the birth of our universe. Scientists continue to explore various possibilities, seeking ways to gather evidence and refine our understanding of the cosmos' earliest moments. The zero-energy universe hypothesis proposes that the total amount of energy in the universe is precisely zero. This concept suggests that the positive energy associated with matter is exactly balanced by the negative energy related to gravity. The universe could have emerged from nothing, as no external energy source would have been required for its creation. This idea challenges our intuitive understanding of the cosmos. We observe a universe filled with galaxies, stars, and planets, all of which possess enormous amounts of energy. However, the zero-energy hypothesis posits that this visible, positive energy is counteracted by an equal amount of negative gravitational energy. Gravity, unlike other forces, is always attractive and operates over vast distances. As the universe expands, it requires energy to overcome this gravitational attraction. The zero-energy hypothesis suggests that this energy requirement exactly matches the positive energy of matter, resulting in a perfect balance. If true, this hypothesis has profound implications for our understanding of the universe's origin and evolution. It provides a potential explanation for how the universe could have spontaneously come into existence without violating the fundamental laws of physics, particularly the conservation of energy. This concept continues to intrigue cosmologists and theoretical physicists as they seek to unravel the deepest mysteries of our universe. Quantum fluctuations represent one of the most intriguing aspects of our universe, challenging our understanding of emptiness itself. In the realm of quantum mechanics, what we perceive as empty space is actually a sea of constant activity. Even in the absence of matter, energy, or any observable particles, the quantum vacuum is never truly empty. At the smallest scales, particles and antiparticles spontaneously pop into existence and then annihilate each other in incredibly short time spans. These fleeting particles, known as virtual particles, are a consequence of the uncertainty principle, which allows for brief violations of energy conservation. This constant flux of creation and destruction gives rise to a background energy that permeates all of space. The concept of quantum fluctuations becomes particularly significant when we consider the origins of our universe. Some theories propose that a quantum fluctuation of sufficient magnitude could have triggered the rapid expansion known as cosmic inflation, essentially creating our entire observable universe from what appears to be nothing. This idea suggests that our vast cosmos, with all its galaxies, stars, and planets, might have emerged from a quantum hiccup in the fabric of space-time. While the notion of something emerging from nothing might seem to defy logic, quantum mechanics repeatedly demonstrates that the behavior of the universe at its most fundamental level often challenges our intuitive understanding of reality. The study of quantum fluctuations continues to push the boundaries of physics, offering tantalizing glimpses into the nature of existence itself and the profound mysteries that lie at the heart of our universe. Virtual particles play a fascinating role in our understanding of the universe's creation. These elusive entities constantly pop in and out of existence throughout the quantum realm, existing for incredibly brief moments before annihilating each other. Their fleeting nature makes them nearly impossible to detect directly, yet their effects are profound. In theories of universe creation, virtual particles take center stage during the earliest moments of the Big Bang. Some cosmologists propose that our entire universe might have begun as a quantum fluctuation, similar to the birth of virtual particles. This idea suggests that the immense energy and matter of our cosmos could have emerged from the quantum vacuum, expanding rapidly to form the universe we observe today. Virtual particles also feature prominently in inflationary theories of the early universe. These models posit that the cosmos underwent a period of exponential expansion shortly after its birth. During this inflation, quantum fluctuations involving virtual particles were stretched to cosmic scales, potentially seeding the large-scale structure we see in the universe today, including galaxy clusters and cosmic voids. Furthermore, virtual particles contribute to our understanding of black holes and their potential role in universe creation. Stephen Hawking's groundbreaking work on black hole radiation relied on the concept of virtual particle pairs forming near a black hole's event horizon. This process could link black holes to the formation of new universes, suggesting that the interior of a black hole might give birth to a new cosmos, with virtual particles acting as the bridge between realities. The simulation hypothesis proposes that our reality, including the entire universe and our consciousness, might be an artificial simulation created by an advanced civilization or intelligence. This concept suggests that what we perceive as the physical world could be a sophisticated computer program, similar to a highly complex video game or virtual reality environment. Proponents of this hypothesis argue that as technology advances, particularly in the fields of computing and artificial intelligence, it becomes increasingly possible to create simulations that are indistinguishable from reality. They reason that if such simulations are possible, it is statistically likely that we are already living in one. The idea draws parallels with philosophical questions about the nature of reality and consciousness. It challenges our understanding of what is real and raises profound questions about the purpose of our existence. Some supporters of the simulation hypothesis even speculate that the creators of the simulation might be able to intervene or alter the parameters of our reality. While the simulation hypothesis remains a topic of debate among philosophers, scientists, and technology experts, it has not been proven or disproven. It serves as a thought-provoking concept that encourages us to question our assumptions about the nature of reality and our place in the universe. The idea that our universe could be a computer simulation is a fascinating concept that has gained traction among some scientists and philosophers. This notion suggests that an incredibly advanced civilization might have the computational power to create a simulated reality so complex and detailed that it encompasses our entire universe. To understand this possibility, we need to consider the rapid advancements in our own computing technology. In just a few decades, we have progressed from simple video games to highly realistic virtual environments. If this trend continues, it is conceivable that future civilizations could create simulations indistinguishable from reality. Proponents of this theory argue that the laws of physics in our universe seem remarkably fine-tuned and mathematical, much like the code underlying a computer program. They also point to the quantized nature of many physical phenomena, which could be analogous to the discrete units of information in a digital simulation. However, it is important to note that this idea remains highly speculative. While it presents an intriguing thought experiment, there is currently no scientific evidence to support the claim that our universe is actually a simulation. The concept continues to spark debate and inspire further research into the nature of reality and consciousness. The simulation hypothesis proposes that our reality might be a computer simulation created by an advanced civilization. This idea has gained traction among philosophers and scientists for several compelling reasons. Technologically, we have seen rapid advancements in computing power and virtual reality. If this trend continues, it is conceivable that future civilizations could create simulations indistinguishable from reality. Some argue that if such simulations are possible, they would likely be numerous, making it statistically probable that we are in one. From a philosophical standpoint, the simulation hypothesis challenges our understanding of consciousness and reality. It raises questions about the nature of our existence and the possibility of multiple levels of simulated realities. This concept aligns with ancient philosophical ideas about the illusory nature of reality, now reframed in technological terms. Scientists point to certain quirks in quantum mechanics, such as the observer effect, as potential evidence for a simulated universe. The idea that reality behaves differently when observed could be seen as a feature of a simulation conserving computing power. Additionally, the discrete nature of many physical phenomena, like energy levels in atoms, could be interpreted as evidence of a digitized reality. The simulation hypothesis and nested universes are intriguing concepts that challenge our understanding of reality. The simulation hypothesis proposes that our universe might be a computer simulation created by an advanced civilization. This idea connects with nested universes in fascinating ways. Imagine a series of Russian nesting dolls, each containing a smaller version inside. Nested universes follow a similar principle, suggesting that our universe could be one of many existing within a larger reality. If we consider the simulation hypothesis in this context, it opens up mind-bending possibilities. A simulated universe could potentially contain its own simulations, creating multiple layers of nested realities. Each level might have its own laws of physics and conscious beings, unaware that their existence is part of a grander simulation. This concept aligns with the idea of nested universes, where each universe is contained within a higher level of reality. The relationship between these ideas raises profound questions about the nature of our existence and the structure of reality itself. It challenges us to consider whether our universe is the outermost layer of reality or just one level in an infinite cascade of simulated or nested universes. The discovery that we live in a simulated universe would profoundly reshape our understanding of reality and our place within it. This revelation would challenge our most fundamental beliefs about the nature of existence and consciousness. One of the most significant implications would be the realization that there must be a creator or creators of our simulation, entities with technology far beyond our current capabilities. This would raise questions about their motives and the purpose of our simulated reality. Are we part of a vast experiment, an entertainment program, or perhaps a tool for learning and development for these advanced beings? Our understanding of physics and the laws that govern our universe would need to be re-evaluated. What we perceive as immutable laws of nature might simply be parameters set by the simulators, potentially subject to change or manipulation. This could open up new avenues for scientific exploration as we attempt to discern the true nature of our simulated reality and possibly even communicate with or influence the simulation itself. The philosophical and ethical implications would be equally profound. Questions of free will, consciousness, and the meaning of life would take on new dimensions. If our reality is simulated, do we possess genuine consciousness, or are we simply complex programs responding to inputs? The boundaries between what we consider real and artificial would blur, potentially altering our perceptions of morality and the value we place on our existence and the existence of others within the simulation. Testing whether our universe is a simulation presents a fascinating challenge for scientists and philosophers alike. One approach involves searching for telltale signs of computational limitations or shortcuts that a simulated universe might exhibit. For instance, we could look for a fundamental unit of time or space analogous to pixels on a screen or the minimum time step in a computer simulation. If we discover such a unit, it could suggest our reality has a discrete digital nature. Another method focuses on identifying patterns or glitches that might arise from the computational nature of a simulated universe. This could include unexpected regularities in physical constants or laws, or even occasional anomalies that resemble software bugs. Scientists might also search for evidence of optimization algorithms, which a simulation might use to conserve computational resources in areas of the universe that are not being directly observed. Some researchers propose that advanced simulations would require vast amounts of energy and computing power. By studying the limits of computation in our universe, we might determine whether it could support a simulation of its own complexity. If we find that our universe lacks the necessary resources to simulate itself, it could suggest that we are not living in a simulation. Ultimately, conclusively proving or disproving the simulation hypothesis remains a significant challenge. Many of these tests rely on assumptions about the nature and capabilities of a potential simulator, which may be fundamentally unknowable to us as inhabitants of the simulation. Nonetheless, these inquiries push the boundaries of our understanding of reality and computation, yielding valuable insights, regardless of their final conclusion. A simulated universe would face several key limitations. Computational power would be a major constraint, limiting the level of detail and complexity that could be modeled. Even with advanced technology, simulating every particle and interaction in a universe would require enormous processing capabilities. The simulation would also be bound by the laws and parameters set by its creators. These might not perfectly mirror our own universe, leading to differences in physics or fundamental constants. This could result in a simulated reality that diverges from our own in subtle or significant ways. Another limitation would be the challenge of simulating consciousness and free will. Creating truly sentient beings within a simulation raises complex philosophical and ethical questions. It might be difficult or impossible to replicate the subjective experience of consciousness in simulated entities. Lastly, there would likely be boundaries to the simulation, both in terms of scale and scope. The creators might focus on certain aspects of the universe while simplifying or omitting others, leading to inconsistencies or areas of limited detail within the simulated world. The simulation hypothesis presents a profound challenge to our perception of reality and consciousness. This concept suggests that our entire universe, including our own thoughts and experiences, might be an elaborate computer simulation created by an advanced civilization. At its core, this idea forces us to question the very nature of our existence. If we are indeed living in a simulated reality, it would mean that everything we perceive as physical and tangible is actually composed of information processed by an incredibly powerful computer system. Our consciousness, which we typically consider the essence of our being, could be nothing more than a complex algorithm running within this simulated environment. This hypothesis also raises intriguing questions about the nature of free will and determinism. In a simulated universe, our actions and decisions might be predetermined by the programming of the simulation, calling into question whether we truly have agency over our choices. Furthermore, it challenges our understanding of physical laws and constants. What we consider immutable laws of nature could simply be parameters set by the creators of the simulation. The implications of the simulation hypothesis extend beyond philosophy into the realm of science and technology. It suggests that the fundamental nature of our reality might be computational rather than physical, potentially revolutionizing our approach to fields such as physics, neuroscience, and artificial intelligence. As we continue to advance our own computing capabilities, the line between simulated and physical reality may become increasingly blurred, further complicating our understanding of consciousness and existence. Dark energy is a mysterious force that permeates all of space and drives the accelerating expansion of our universe. Discovered in the late 1990s, this invisible energy accounts for roughly 68% of the total energy in the cosmos. Unlike gravity, which pulls matter together, dark energy acts as a repulsive force, pushing galaxies and galaxy clusters apart at an ever-increasing rate. Scientists have proposed several theories to explain dark energy, but its true nature remains elusive. One possibility is that it represents the energy of empty space itself, a concept known as vacuum energy. Another idea suggests that dark energy might be a new type of dynamical energy field that varies in strength over time and space. The effects of dark energy become more prominent on the largest cosmic scales. While gravity dominates the behavior of matter within galaxies and galaxy clusters, dark energy takes over in the vast voids between these structures. As the universe continues to expand, the influence of dark energy grows stronger, potentially leading to a future where galaxies become increasingly isolated. Understanding dark energy is crucial for cosmologists as they attempt to unravel the ultimate fate of our universe. Its study combines observational astronomy, theoretical physics, and advanced technologies, making it one of the most exciting and challenging frontiers in modern science. Dark energy plays a crucial role in the expansion of the universe, acting as a mysterious force that pushes everything apart. Unlike gravity, which pulls matter together, dark energy exerts a repulsive force that causes the universe to expand at an ever-increasing rate. Scientists discovered this accelerating expansion in the late 1990s by observing distant supernovae. They found that these exploding stars were farther away than expected, indicating that the universe was expanding faster than previously thought. This led to the hypothesis of dark energy as the driving force behind this acceleration. Dark energy affects the expansion of the universe uniformly across all space. As the universe grows larger, the influence of dark energy becomes more dominant. This is because the density of matter decreases as space expands, while the density of dark energy remains constant. Consequently, the expansion of the universe continues to speed up over time. The nature of dark energy remains one of the biggest mysteries in modern cosmology. Scientists estimate that it makes up about 68% of the total energy content of the universe, yet its fundamental properties are still unknown. Understanding dark energy and its effects on cosmic expansion is crucial for predicting the ultimate fate of our universe. Dark energy remains one of the most perplexing mysteries in modern cosmology. This invisible force, which appears to permeate all of space, is causing our universe to expand at an accelerating rate. While scientists have observed its effects, the true nature of dark energy continues to elude us. The idea that dark energy could serve as a bridge to other universes is an intriguing speculation that has captured the imagination of some theoretical physicists. This concept stems from the multiverse theory, which proposes the existence of multiple universes beyond our own. In this framework, dark energy might be a manifestation of interactions between our universe and others. However, it is crucial to note that this idea remains highly speculative and lacks empirical evidence. Current scientific understanding does not provide a mechanism for dark energy to act as a physical bridge between universes. The challenge lies in the fact that other universes, if they exist, would likely be entirely separate from our own, with no means of direct observation or interaction. While the notion of dark energy as a cosmic bridge is captivating, scientists continue to focus on understanding its fundamental properties within our observable universe. Ongoing research and future experiments may shed light on the true nature of dark energy and potentially reveal unexpected connections to the fabric of reality beyond our cosmic horizon. The Big Rip scenario is a dramatic theory about the potential fate of our universe. It suggests that the expansion of the universe will accelerate to such an extreme degree that it will eventually tear apart everything in existence. This cosmic apocalypse would start with the largest structures, like galaxy clusters and galaxies, before moving on to star systems, planets, and even atoms themselves. This theory is closely tied to our understanding of dark energy, the mysterious force that appears to be driving the accelerating expansion of the universe. In the Big Rip scenario, dark energy would become increasingly powerful over time, overwhelming the fundamental forces that hold matter together. The key to this theory lies in a property of dark energy called the equation of state. If this value drops below -1, it could lead to a situation where the density of dark energy increases as the universe expands, creating a runaway effect. This would cause the expansion to accelerate faster and faster, eventually reaching a point where the fabric of space-time itself would be torn apart. While the Big Rip is a fascinating possibility, it remains a speculative idea. Current observations suggest that the equation of state for dark energy is close to, but not below, -1. However, ongoing research and future observations may provide more clarity on the long-term behavior of dark energy and the ultimate fate of our universe. Dark energy plays a crucial role in shaping the long-term fate of our universe. This mysterious force, which accounts for about 68% of the total energy in the cosmos, exerts a repulsive effect that counteracts gravity. As the universe continues to expand, dark energy becomes increasingly dominant, accelerating the expansion at an ever-growing rate. The influence of dark energy on our cosmic future is profound. If it maintains its current properties, the universe will likely experience a phenomenon known as the Big Freeze. In this scenario, the accelerating expansion will cause galaxies to move apart at speeds faster than light, making them invisible to one another. Over incredibly vast timescales, even individual stars and planets within galaxies will separate, leaving the universe as an immensely vast, cold, and dark expanse. This expansion driven by dark energy could also lead to the Big Rip, a more extreme outcome. In this case, the repulsive force of dark energy might become so powerful that it overcomes all other forces, literally ripping apart galaxies, solar systems, planets, and even atoms. The universe would end in a violent, all-encompassing tear in the fabric of space-time itself. However, our understanding of dark energy is still limited, and its properties might change over time. If dark energy weakens, the expansion could slow down or even reverse, potentially leading to a big crunch where the universe collapses back in on itself. The nature and behavior of dark energy thus hold the key to unraveling the ultimate destiny of our cosmos. Dark energy remains one of the most perplexing mysteries in modern cosmology. Scientists have proposed several theories to explain its nature and origin, each attempting to unravel the enigma of this invisible force that appears to be driving the accelerating expansion of our universe. One prominent theory suggests that dark energy is a property of space itself, a sort of cosmic anti-gravity that becomes more powerful as the universe expands. This concept, known as the cosmological constant, was first proposed by Albert Einstein and later abandoned, only to be revived in light of recent observations. It posits that empty space has an intrinsic energy that pushes the cosmos apart. Another intriguing possibility is that dark energy is a new type of dynamical energy, fluid or field that fills all of space. Unlike the cosmological constant, which is unchanging, this form of dark energy might vary in time and space. Some scientists have dubbed this theoretical field quintessence, drawing inspiration from the ancient Greek concept of a fifth element permeating the universe. Some researchers propose more radical explanations, suggesting that our understanding of gravity itself might be flawed. These modified gravity theories attempt to explain the observed cosmic acceleration without invoking dark energy at all, instead positing that gravity behaves differently on vast cosmic scales than it does in our local universe. Dark energy presents a profound challenge to our understanding of physics, pushing the boundaries of our current knowledge about the fundamental nature of the universe. This mysterious force, which appears to permeate all of space, is causing the expansion of the universe to accelerate, contrary to what scientists originally expected. The concept of dark energy contradicts our long-held assumptions about gravity. According to traditional physics, the expansion of the universe should be slowing down due to the gravitational pull between galaxies. However, observations of distant supernovae in the late 1990s revealed that the universe is expanding at an increasing rate, suggesting the presence of an unknown force counteracting gravity. This discovery has far-reaching implications for our understanding of the cosmos. Dark energy is estimated to make up about 68% of the total energy content of the universe, yet we cannot directly observe or measure it. Its properties seem to violate our current laws of physics, suggesting that our theories of gravity and quantum mechanics might be incomplete. Furthermore, dark energy raises questions about the ultimate fate of the universe. If it continues to drive accelerated expansion, it could lead to a scenario where galaxies become so distant from each other that they are no longer observable from Earth, fundamentally changing our view of the cosmos. This enigmatic force continues to baffle scientists, spurring new research and potentially revolutionary theories that could reshape our understanding of the universe. Dark energy remains one of the most enigmatic phenomena in modern cosmology. This mysterious force, responsible for the accelerating expansion of our universe, has puzzled scientists since its discovery in the late 1990s. While we understand its effects, the true nature of dark energy continues to elude us, leading to intriguing speculations about its origin. Some theorists have proposed that dark energy could indeed be evidence of forces originating from beyond our observable universe. This concept ties into ideas from string theory and the multiverse hypothesis, suggesting that our universe might be just one of many in a vast cosmic landscape. In this scenario, the effects we observe as dark energy could be the result of interactions between our universe and others existing in higher dimensions or parallel realities. However, it is crucial to note that these ideas remain highly speculative and lack concrete observational evidence. The scientific community continues to explore various explanations for dark energy, ranging from modifications to Einstein's theory of general relativity to the existence of new fundamental particles or fields within our own universe. As our understanding of the cosmos deepens and our observational capabilities improve, we may eventually unravel the true nature of dark energy. Whether it originates from beyond our universe or arises from yet undiscovered properties within it, the quest to explain dark energy remains at the forefront of cosmological research, driving us to explore the boundaries of our knowledge and pushing the limits of our understanding of the universe. Cosmic topology explores the shape and structure of the universe on the largest scales. It delves into questions about whether space is finite or infinite, flat or curved, and whether it connects back on itself in complex ways. This field combines aspects of cosmology, geometry, and physics to understand the fundamental nature of the cosmos. Astronomers and cosmologists use observations of the cosmic microwave background radiation, and large-scale structures to gather clues about the universe's topology. They look for patterns or repetitions that might indicate a particular shape or size to the universe. For instance, if the universe were shaped like a giant donut, we might see the same patterns of galaxies repeating in different directions. The concept of cosmic topology challenges our everyday perceptions of space. While we experience the world around us as essentially flat and infinite, the universe might have a more intricate structure. It could be curved in higher dimensions or have boundaries that wrap around, similar to how the surface of Earth is finite but has no edge. Understanding cosmic topology could have profound implications for our comprehension of the universe's origin, evolution, and ultimate fate. It might help explain certain cosmological puzzles and provide insights into the nature of space and time themselves. As we continue to gather more precise observations and develop more sophisticated models, we edge closer to unraveling this cosmic mystery. The shape of the universe is a fundamental aspect that influences our understanding of what might exist beyond its boundaries, if such boundaries even exist. Cosmologists have proposed several possible geometries for the universe: flat, closed, or open. Each of these shapes carries profound implications for what we might consider to be beyond the observable universe. In a flat universe, which current observations suggest is most likely, space extends infinitely in all directions. This means there might not be an outside or beyond in the traditional sense. Instead, the universe could continue endlessly, potentially containing an infinite number of galaxies and structures beyond what we can observe. A closed universe, often visualized as the surface of a sphere, would be finite but unbounded. In this scenario, if one could travel far enough in any direction, they would eventually return to their starting point. The concept of beyond becomes more complex here as the universe loops back on itself. An open universe would have a hyperbolic geometry, expanding forever at an accelerating rate. In this case, the beyond might be an ever-expanding frontier of space, constantly pushing outward faster than light can travel. This would create regions forever out of reach, perpetually beyond our observable universe. The shape of our universe is a fascinating topic in cosmology. Current theories propose three main possibilities for the geometry of the universe: flat, closed, or open. Each of these geometries has profound implications for the nature and fate of our cosmos. A flat universe is like an infinite sheet of paper, extending endlessly in all directions. In this scenario, parallel lines never meet, and the universe has no boundaries. Most current observations suggest our universe is very close to being flat, if not exactly flat. A closed universe, on the other hand, is finite, but has no boundaries, much like the surface of a sphere. If you travel far enough in one direction, you would eventually return to your starting point. In this geometry, parallel lines would eventually converge. The third possibility is an open universe, which has a hyperbolic geometry. This can be visualized as a saddle shape, where parallel lines diverge. An open universe would continue expanding forever, becoming increasingly sparse. The curvature of space-time and cosmic topology are deeply interconnected concepts that shape our understanding of the universe's structure. Space-time curvature, a fundamental aspect of Einstein's theory of general relativity, describes how massive objects warp the fabric of space and time around them. This curvature affects the paths of light and matter, creating what we perceive as gravity. Cosmic topology, on the other hand, deals with the overall shape and connectivity of the universe on the largest scales. The curvature of space-time plays a crucial role in determining this topology. Depending on the average density of matter and energy in the universe, space-time can have positive, negative, or zero curvature, each leading to different possible topologies for the cosmos. In a universe with positive curvature, space-time bends back on itself, potentially creating a closed, finite universe. This could result in a spherical or more complex topology, where traveling in one direction might eventually bring you back to your starting point. Conversely, negative curvature could lead to an open, infinite universe with a hyperbolic geometry, offering a vast array of possible paths through space. The case of zero curvature, which current observations suggest is the most likely scenario for our universe, results in a flat topology. In this model, parallel lines remain parallel indefinitely, and the universe could be infinite in extent. However, even a flat universe could have a complex topology, potentially being folded or connected in ways that are challenging to detect from our vantage point within it. Our understanding of the universe's topology comes from a combination of astronomical observations and theoretical models. One key piece of evidence comes from the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. Scientists have carefully mapped this radiation, looking for patterns that might indicate a finite or curved universe. So far, these observations suggest that the universe is remarkably flat and possibly infinite in extent. Another line of evidence comes from the distribution of galaxies on the largest scales. If the universe had a compact topology, we might expect to see repeating patterns in the arrangement of galaxy clusters. However, surveys of the sky have not revealed any such patterns, supporting the idea of a vast, possibly infinite universe. Gravitational lensing, the bending of light by massive objects, also provides clues about the shape of space. The way distant galaxies are distorted by intervening matter helps scientists map out the curvature of space-time. These observations align with the concept of a flat universe, though they don't rule out slight curvatures on the largest scales. It's important to note that our observations are limited by the observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang. This means we can't directly observe what lies beyond this cosmic horizon, leaving some uncertainty about the true global topology of the universe. A finite but unbounded universe and an infinite universe present fundamentally different concepts when considering what lies beyond. In a finite but unbounded universe, the idea of beyond becomes a complex notion. Imagine walking on the surface of a sphere like Earth. You can travel in any direction without ever reaching an edge or boundary, yet the surface area remains finite. Similarly, a finite but unbounded universe would have no edge or outside to explore. This contrasts sharply with an infinite universe, which extends endlessly in all directions. In an infinite universe, there would always be more space, more galaxies, and more matter no matter how far one travels. The concept of beyond in this case simply means more of the same, stretching out infinitely. The finite but unbounded model challenges our intuition about space. It suggests that if you could travel in a straight line long enough, you might return to your starting point, much like circumnavigating the globe. An infinite universe, on the other hand, aligns more closely with our everyday experience of space, extending in all directions. These different models have profound implications for the nature of space, the distribution of matter, and the ultimate fate of the universe. While current observations favor an infinite or extremely large universe, the true nature of what lies beyond remains one of the most intriguing questions in cosmology. The concept of a wraparound universe challenges our understanding of space and its boundaries. Imagine a cosmic landscape where traveling in one direction eventually brings you back to your starting point, much like circumnavigating the Earth. This idea suggests that our universe might not have an edge or an outside in the conventional sense. In a wraparound universe, what we perceive as vast, possibly infinite space, could actually be finite but unbounded. This means that light and matter could theoretically traverse the entire universe and return to their origin point, given enough time. Such a concept fundamentally alters our perception of what lies beyond our observable universe. This model of the cosmos raises intriguing questions about the nature of space itself. If the universe wraps around, it implies that the fabric of space-time might be curved on a cosmic scale, forming a shape akin to a multidimensional torus or a more complex geometric structure. This curvature would be imperceptible on smaller scales, but would become apparent when considering the universe as a whole. The wraparound universe concept challenges our intuitive notions of beyond and infinity. It suggests that there might not be an outside to our universe at all, but rather a continuous, self-contained system. This idea forces us to reconsider our place in the cosmos and the very nature of space and time, pushing the boundaries of our cosmic understanding. Cosmic topology and the multiverse theory are interconnected concepts that explore the fundamental nature and structure of our universe. Cosmic topology examines the overall shape and connectivity of space, questioning whether our universe is flat, curved, or has a more complex geometric structure. This field of study investigates the possibility that space might be finite yet boundless, similar to the surface of a sphere, or even have unusual connections between distant regions. The multiverse theory, on the other hand, proposes the existence of multiple universes beyond our own. These universes could have different physical laws, dimensions, or initial conditions. One way the multiverse concept relates to cosmic topology is through the idea of cosmic inflation, a theory suggesting that our universe underwent a period of rapid expansion in its earliest moments. Some models of cosmic inflation predict that this process could create multiple bubble universes, each with its own cosmic topology. These bubbles might have different geometries, sizes, or even different dimensions. In this scenario, our observable universe would be just one bubble in a vast foam of universes, each with its unique topological properties. Furthermore, certain approaches to quantum mechanics and string theory also support the multiverse concept, suggesting that different universes might exist in higher dimensions or parallel realities. These ideas expand our understanding of cosmic topology beyond the confines of our observable universe, challenging us to consider the shape and structure of reality on an even grander scale. The anthropic principle is a thought-provoking concept in cosmology that addresses the apparent fine-tuning of our universe. It suggests that the fundamental constants and laws of physics seem precisely calibrated to allow for the existence of life as we know it. This principle comes in two main forms: the weak anthropic principle and the strong anthropic principle. The weak anthropic principle states that we observe a universe compatible with our existence simply because we could not exist to observe it otherwise. It is a logical statement that does not make claims about why the universe is the way it is, but rather points out that our observations are necessarily biased by our own existence. The strong anthropic principle goes further, proposing that the universe must have properties that allow life to develop within it at some stage. This version has led to various interpretations, including the idea of a multiverse where our universe is just one of many with different physical constants. Critics argue that the anthropic principle is not truly explanatory and may lead to circular reasoning. Supporters, however, see it as a valuable tool for understanding our place in the cosmos and the seemingly improbable conditions that allow for our existence. The debate surrounding the anthropic principle continues to spark discussions about the nature of our universe and our role as observers within it. The fine-tuning of universal constants is a fascinating concept that bridges our understanding of our universe with speculations about what might lie beyond. These constants, such as the strength of gravity or the speed of light, appear to be precisely calibrated to allow for the existence of complex structures like galaxies, stars, and ultimately, life as we know it. This apparent fine-tuning has led scientists to ponder whether our universe is unique or part of a larger cosmic landscape. One theory that attempts to explain this fine-tuning is the multiverse hypothesis. This idea suggests that our universe is just one of many, possibly infinite, universes. In this scenario, each universe might have different values for its fundamental constants. We find ourselves in a universe with constants that allow for our existence simply because we could not exist in universes with different values. This concept, known as the anthropic principle, provides a potential explanation for the apparent fine-tuning without requiring a purposeful designer. Another intriguing possibility is the idea of cyclical universes. Some theories propose that universes might go through cycles of expansion and contraction, with each cycle potentially having slightly different constants. Over countless cycles, a universe with the right conditions for complexity and life might eventually emerge. This concept connects the fine-tuning we observe to a larger cosmic history beyond our observable universe. These theories about what lies beyond our universe remain speculative, as we cannot directly observe or test them. However, they demonstrate how the puzzle of fine-tuned constants pushes the boundaries of our cosmological understanding, encouraging scientists to think beyond the confines of our observable universe and consider the broader context in which our cosmos might exist. The multiverse solution to the fine-tuning problem offers a fascinating perspective on the fundamental constants and laws that govern our universe. This concept suggests that our universe is just one of many, perhaps even an infinite number, existing simultaneously. Each of these universes might have different physical laws and constants, creating a vast array of possible realities. In our universe, we observe that certain fundamental constants appear to be incredibly fine-tuned for the existence of complex structures, including life as we know it. Even slight variations in these constants could result in a universe incapable of supporting stars, planets, or the complex chemistry necessary for life. This apparent fine-tuning has led some to question whether our universe was designed with a specific purpose. The multiverse solution proposes that, given a large enough number of universes with varying properties, it becomes statistically likely that at least one would have the precise conditions necessary for life. In this view, we simply happen to exist in one of the universes capable of supporting our form of life, while countless others may be sterile or have entirely different forms of complexity. This explanation addresses the fine-tuning problem by suggesting that our universe is not uniquely designed, but rather one of many possibilities in a vast cosmic landscape. It shifts the question from why our universe is fine-tuned to why we observe ourselves in a universe capable of supporting our existence, which can be explained by the anthropic principle. We can only observe universes compatible with our existence. The anthropic principle offers a fascinating perspective on the nature of our universe and our place within it. This principle observes that the physical laws and constants of our universe appear to be finely tuned to allow for the existence of life as we know it. Even small changes to these fundamental parameters could result in a universe incapable of supporting complex structures, let alone conscious beings. Proponents of intelligent design often point to the anthropic principle as evidence of a cosmic architect, arguing that such precise calibration suggests intentional creation. They contend that the odds of a life-supporting universe arising by chance are so astronomically low that design becomes the most plausible explanation. However, many scientists and philosophers interpret the anthropic principle differently. They argue that it may simply be an observational bias. We observe a universe compatible with our existence because that is the only type of universe in which we could exist to make such observations. This interpretation aligns with the concept of a multiverse, where our universe is just one of countless others with varying physical laws. The anthropic principle thus presents a conundrum. While it highlights the remarkable conditions necessary for our existence, it does not definitively prove or disprove design. Instead, it prompts us to consider deeper questions about the nature of reality, the limits of our understanding, and our place in the cosmos. As we continue to explore these profound ideas, the anthropic principle remains a thought-provoking concept at the intersection of physics, philosophy, and our quest to understand the universe. The anthropic principle comes in two main forms: the weak anthropic principle and the strong anthropic principle. Both address the apparent fine-tuning of our universe for life, but they differ in their implications and scope. The weak anthropic principle states that the observable properties of the universe must be compatible with the existence of conscious observers like us. It suggests that we should not be surprised to find ourselves in a universe that allows for our existence, as we could not observe a universe incompatible with our existence. This version is more widely accepted in the scientific community as it makes fewer assumptions and aligns with our current understanding of physics and cosmology. The strong anthropic principle, on the other hand, makes a bolder claim. It proposes that the universe must have the properties that allow life to develop within it at some stage in its history. This version suggests that the fundamental constants and laws of physics are somehow constrained to values that permit the emergence of conscious observers. Some interpretations of the strong anthropic principle even propose that the universe was designed with the specific purpose of creating life. While the weak anthropic principle is generally seen as a logical observation, the strong version remains more controversial. It raises questions about the nature of reality, the possibility of multiple universes, and the role of consciousness in the cosmos. These ideas continue to fuel debates among scientists and philosophers as we strive to understand our place in the universe. Testing or falsifying the anthropic principle presents significant challenges due to its nature as a philosophical and cosmological concept rather than a straightforward scientific theory. However, scientists and philosophers have proposed several approaches to examine its validity and implications. One potential method involves studying the fundamental constants of physics. If we could observe or detect other universes with different physical constants, it might challenge the strong anthropic principle, which suggests our universe is fine-tuned for life. Advanced particle accelerators or astronomical observations could potentially reveal evidence of other universes or dimensions with different physical laws. Another approach focuses on exploring the limits of life as we know it. By discovering organisms that thrive in extreme environments or developing artificial life forms that operate under different physical conditions, we might expand our understanding of what constitutes a life-supporting universe. This could weaken the anthropic argument that our universe is uniquely suited for life. Computer simulations of universe formation under varying conditions could also provide insights. If simulations consistently produce universes capable of supporting complex structures or lifelike processes, it might suggest that our universe is not as finely tuned as the anthropic principle implies. Conversely, if life-supporting universes prove to be extremely rare in these simulations, it could lend support to anthropic arguments. The anthropic principle raises profound questions about the nature of our universe and our place within it. This principle suggests that the fundamental constants and laws of physics in our universe are finely tuned to allow for the existence of life as we know it. If these constants were even slightly different, the universe might not have developed in a way that could support complex structures like stars, planets, and ultimately, conscious observers like ourselves. This observation leads to two main interpretations. The first is that our universe is indeed unique and specially crafted to support life, potentially implying a purposeful design. The second interpretation, which aligns with current scientific thinking, suggests the existence of a vast multiverse containing countless universes with different physical laws and constants. In the multiverse scenario, our universe is not unique, but rather one of many. We observe it as life-supporting simply because we could not exist in universes with different parameters. This view resolves the apparent fine-tuning without resorting to notions of design, but it also implies that the vast majority of universes in the multiverse would be sterile and incapable of supporting life. The anthropic principle thus challenges our understanding of cosmic uniqueness. While our universe might be just one of many, the conditions that allow for our existence remain remarkably specific, underscoring the delicate balance that enables life to flourish in the cosmos we observe. The anthropic principle and observer-created reality are interconnected ideas that explore our place in the universe and how we perceive it. The anthropic principle suggests that the fundamental constants and laws of our universe appear fine-tuned to allow for the existence of life and conscious observers like ourselves. This concept proposes that we observe the universe the way it is, because if it were different, we would not be here to observe it. Observer-created reality, on the other hand, delves into the fascinating realm of quantum mechanics. It posits that the act of observation can influence the outcome of quantum events. This idea stems from experiments showing that particles can exist in multiple states simultaneously until they are observed or measured, at which point they collapse into a definite state. When we combine these concepts, we encounter a thought-provoking perspective on reality. If our observations can influence the quantum world and our existence is tied to specific universal constants, it raises questions about the nature of reality itself. Are we merely fortunate observers in a universe that happens to support our existence, or does our presence as conscious beings play a more fundamental role in shaping the reality we perceive? This intersection of ideas challenges our understanding of cause and effect in the cosmos. It suggests a complex interplay between the observer and the observed, blurring the lines between objective reality and subjective experience. As we continue to explore these concepts, we may gain deeper insights into the fundamental nature of our universe and our place within it. Our understanding of time is deeply rooted in our observations of the universe we inhabit. However, when we consider what might exist beyond our universe, our familiar concepts of time may no longer apply. In our universe, time is intricately linked with space in what scientists call spacetime, a fundamental fabric that underlies everything we observe. Beyond our universe, if other universes or realms exist, they might operate under entirely different physical laws. These hypothetical realms could have their own unique temporal structures, or perhaps no concept of time at all. Some theoretical physicists propose the existence of higher dimensions where time as we know it might be just one of many temporal dimensions. Another intriguing possibility is that time itself might be an emergent property of our universe, arising from more fundamental phenomena. In this scenario, whatever exists beyond our universe might be governed by principles so alien to our understanding that our notion of time would be meaningless there. It is important to note that these ideas remain highly speculative. Our current scientific methods and instruments are limited to observing and measuring phenomena within our universe. The nature of time beyond our cosmic boundaries remains one of the most profound and elusive questions in modern physics and cosmology. Eternal inflation is a cosmological theory that proposes our universe is part of a much larger, ever-expanding multiverse. This concept suggests that space is constantly expanding at an exponential rate, creating new regions that become separate universes. In this model, inflation never truly ends. It continues indefinitely in some areas while stopping in others, leading to the formation of countless bubble universes. The idea of eternal inflation challenges our understanding of time beyond our observable universe. In regions where inflation continues, time might flow differently or even lose its meaning as we know it. These areas experience such rapid expansion that conventional notions of cause and effect break down. As a result, time in these eternally inflating regions could be fundamentally different from the linear time we experience in our universe. Furthermore, eternal inflation implies that our universe might be just one of infinitely many, each with its own timeline. This raises profound questions about the nature of time on a multiverse scale. If multiple universes exist simultaneously, each with its own temporal flow, how do we reconcile these different timelines? The concept suggests that time as we understand it might be limited to our specific universe, with other realms potentially experiencing entirely different temporal structures. Eternal inflation also presents the possibility that time itself had no beginning. In this scenario, the process of universe creation has always been occurring and will continue indefinitely. This challenges the notion of a singular starting point for time and space, suggesting instead an eternal cycle of universe formation without a definitive beginning or end. Time, as we understand it in our universe, might behave in radically different ways in other universes or dimensions. In some theoretical frameworks, time could flow backwards or even sideways, defying our conventional understanding of cause and effect. Imagine a universe where the future influences the past, creating a cosmic loop of intertwined events. In other possible universes, time might not exist as a dimension at all. Instead, all events could occur simultaneously, with no discernible sequence or progression. This concept challenges our fundamental perception of reality and raises intriguing questions about the nature of existence and consciousness in such a realm. Some theoretical physicists propose the existence of universes with multiple time dimensions. In these scenarios, beings might experience several different timelines concurrently, navigating a complex web of temporal pathways. This could lead to fascinating phenomena, such as the ability to move freely between different points in time, much like we move through space in our universe. Another possibility is that time in other universes might flow at vastly different rates compared to our own. A second in one universe could equate to millennia in another, or vice versa. This variation in temporal flow could have profound implications for the development of life, the evolution of cosmic structures, and the ultimate fate of these alternative universes. The block universe theory proposes that our reality exists as a four-dimensional structure, with time as the fourth dimension alongside the three spatial dimensions we experience. In this view, past, present, and future all exist simultaneously, much like different locations coexist in space. This concept challenges our intuitive understanding of time as a flowing entity and suggests that change is an illusion created by our limited perception. Relating to concepts of beyond, the block universe theory opens up intriguing possibilities. If all of time exists at once, it implies that what we consider the future is already set, just as the past is fixed. This idea extends our notion of reality beyond our current moment, encompassing all of history and all that is yet to come in a single, unchanging structure. Furthermore, the block universe concept raises questions about what might exist outside this four-dimensional construct. Could there be other block universes with different physical laws or dimensions? This speculation leads us to contemplate realms beyond our observable universe, potentially infinite in scope and variety. The theory also connects to ideas of determinism and free will, pushing us to reconsider our place in the cosmos. It suggests that our actions, while feeling spontaneous to us, might be predetermined parts of the universal structure. This perspective encourages us to look beyond our immediate experiences and consider our existence as part of a vast, interconnected whole. The arrow of time, which points from the past to the future, is a fundamental aspect of our universe that shapes our understanding of causality and the evolution of cosmic structures. When we consider what might exist beyond our observable universe, this concept becomes even more intriguing. Some theories suggest that regions beyond our cosmic horizon might experience time differently. These areas could have their own local arrows of time, potentially flowing in different directions or at different rates compared to our observable universe. This idea challenges our conventional understanding of cause and effect on a cosmic scale. Multiverse theories propose the existence of multiple universes, each potentially with its own unique laws of physics and temporal properties. In some of these hypothetical universes, time might flow backwards or not exist as we know it at all. The arrow of time in our universe is closely tied to the increase of entropy, but other universes might operate under different thermodynamic principles. The concept of eternal inflation, which posits that our universe is just one bubble in an ever-expanding cosmic foam, introduces the possibility of regions where time behaves in ways we can scarcely imagine. In these scenarios, the arrow of time could be a local phenomenon, specific to our particular cosmic bubble, rather than a universal constant. Timelessness beyond our universe challenges our fundamental understanding of existence. In our cosmos, time is a dimension woven into the fabric of space-time, governing the sequence of events and the flow of causality. However, the concept of timelessness suggests a realm where this dimension simply does not exist. In such a timeless state, there would be no before or after, no cause and effect as we understand it. All moments, if they could be called that, would exist simultaneously. This is difficult for our time-bound minds to grasp, as we are accustomed to experiencing reality as a series of sequential events. Some theories propose that time itself might have emerged with our universe during the Big Bang. If this is the case, then whatever exists beyond our universe might exist in a state free from temporal constraints. This could mean that other universes or higher dimensional spaces operate under entirely different rules, where our concept of time has no meaning. The implications of timelessness are profound. It could mean that questions about the beginning or end of existence become meaningless. In a timeless realm, there would be no aging, no decay, and no change as we understand it. The very notion of existence might take on an entirely different meaning, challenging our most basic assumptions about reality. Theories about the origin of time are deeply intertwined with our understanding of the universe and what might exist beyond it. As we explore these concepts, we must consider that our perception of time might be limited to our observable universe. Some theories suggest that time began with the Big Bang, marking the start of our universe. However, this raises questions about what came before and what might exist outside our cosmic bubble. Multiverse theories propose that our universe could be one of many, each with its own set of physical laws and potentially its own version of time. The concept of eternal inflation presents the idea that our universe is part of an ever-expanding cosmic landscape where new universes are constantly forming. In this scenario, time as we know it might only apply to our local region, while other universes could experience time differently or not at all. Quantum theories offer another perspective, suggesting that time might emerge from more fundamental quantum processes. This could mean that beyond our universe, entirely different mechanisms govern the flow of events, challenging our very notion of time's existence. The concept of realms beyond our universe is a fascinating topic that pushes the boundaries of our understanding. While we cannot directly observe or confirm the existence of such realms, theoretical physics offers some intriguing possibilities. In our universe, cause and effect are fundamental principles that govern how events unfold. However, some theories suggest that in other hypothetical universes or dimensions, these principles might operate differently or not apply at all. For instance, in certain interpretations of quantum mechanics, particles can appear to influence each other instantaneously across vast distances, seemingly defying our classical understanding of cause and effect. Some physicists propose the idea of a multiverse, where numerous universes exist alongside our own, each potentially governed by different physical laws. In these alternate universes, the very fabric of reality could be fundamentally different, allowing for phenomena that would seem impossible in our world. It is important to note that these ideas remain highly speculative and are not currently testable with our existing technology. However, they continue to inspire scientists and push the boundaries of theoretical physics, encouraging us to question our assumptions about the nature of reality and causality.